All right. So this is one of the interesting part of physics. In this one, we're going to be dealing with circular motion. The recording has started, so it will be shared to the class. Okay. So we'll deal with circular motion. We're dealing with circular motion, which is actually a very critical part you want to learn in practical physics. Remember when we were in school and we did this in the lab? We always calculated simple pendulum or calculated how motion is moving and all that. Yes. So this is it. This is one of the things we're going to be applying. I'll teach you the basic roots, then you can apply the basic roots. The same thing I did for maths class. I'll teach you the basic roots, and once you see any question, you already know how to tackle it. So, and for those of you asking for those of you asking for the maths class and all, that was a paid session, but I'll see how I can make those recordings available. Because if I just make it available like that, you know, those who paid for it are going to kill me. All right. So yes, the secular. I'll still see how I can post it. The secular motion. All right. So um, let's do. All right. Circular motion. All right. So what is circular motion? Circular motion is defined as the motion of an object round a circle. Okay. So that is circular motion, the motion of an object around a circle or circular path. All right. So if you see an object, one second. If you see an object going, if you see something traveling around a circle like this, change it to white. Thank you. Uh-huh. And you are white. So now the motion of an object, let's say this is our object here. Let this be our object. And it is actually traveling around the circle or going in a circular path. All right. That's what circular motion is. Now, an object can undergo what we call a uniform circular motion when it is moving along a circular path at constant speed. All right, so it is moving along a circular path at constant speed. All right, so now circular motion has three basic characteristics, and that's what you're going to learn. Now, please take a look at this, guys. This motion is moving, this object is moving around the circular motion. And if you notice something, what has happened is it has subtended an angle. Trust me. You understand the concept of circular motion? You are good to go. You have no problems at all. You are good to go. So now, the first we need to know is the constant speed in circular motion. The second we need to know is the changing of variable velocity. And the third thing we need to know is centripetal acceleration, which we're going to be looking at um, very well. There's centripetal acceleration and centripetal force. Okay, so when an object is undergoing circular motion and this circular motion most times is directly centered towards the, or is directed towards the center, all right? It's directed towards the center of the circular path. It uses what we call the centripetal acceleration. So I'm going to start with centripetal acceleration. So it uses what we call the please don't mind my handwriting, as in I'm just very tired. So centripetal. acceleration. All right, don't worry. You're going to grab all this, and that's my job. Make sure you understand it. So we have the centripetal acceleration, and for the centripetal acceleration, A equals v square over r. Take note of that formula. A equals v square over r. Okay. So now v is the speed or v is the velocity, while r is the radius of circular path. So you see this radius here in a circle from any line drawn from the center of the circle to any part of the circumference is our r. So this is the r because it is this motion here is directed towards the center of this circular path. So it is going to be observing what we call the centripetal acceleration, and that is how we calculate the centripetal acceleration. Now, there is a force that keeps this object, this particular object, moving along the circular path. There is a force that is making it to move along this circular path. That force, okay, there's a force making it to move along the circular path. All right, that force is what we call the centripetal force. So we have centripetal acceleration and we have the centripetal force. So it is what we call the centripetal force. All right, the centripetal force. And we already know that force is equal to mass times acceleration. Well, for those that were not here, no, because I'm saying we already know because we've already, one second, because we've already kind of treated that. I don't even know where that physics class is. I think it's gone to hide. This is just the maths on the physics on. We treated that the force times acceleration. Hmm, okay, well, let's come back here. I'll find the physics board or the part. So force actually is equal to force. Our force is equal to mass times acceleration. Okay, so this is the standard formula for force. It's mass times acceleration. We used Newton's second law in physics class then to prove this, and we had a great understanding about this. So now, since we know that force is equal to mass times acceleration, centripetal force then, that's the centripetal force will be equal to our mass times the centripetal acceleration, which is um, centripetal acceleration. And this is going to give us the mass times, remember centripetal acceleration is v squared over r, okay? And then we have mv squared over r. So remember, the centripetal force keeps the object, is the force that keeps an object moving along a circular path, all right, at constant speed, while the centripetal acceleration is experienced by any object that is undergoing this circular motion, all right? And it's directed towards the center of the circular path. Okay, so that is the centripetal acceleration. So let us try to take some questions. We take some examples and some questions so that you can have a clear understanding before we move into this big guy called simple harmonic motion. And mind you, simple harmonic motion, you need to know the various applications of it. So we'll be treating multiple examples on simple harmonic motion just so we can get the basics because it has close to 11 formulas. So you need to know it. And don't worry, those 11 formulas are relatable. Once you know the basic concept of it, you already know which one to apply. You already know how you want to apply it. So it's very simple. All right. Don't worry about the amount of formulas it has. The formulas in physics can mix up. Okay, but it's just that they're applicable anywhere. Let's try this question first. Let's say we have um okay, so this one says okay, this one says an object of weight 150 Newton moves with a speed of 4.5 meter per second in a circular path of radius 3 meters. Right, so it's telling us calculate its centripetal acceleration and the magnitude of the centripetal force. So take our gravity equals 9.8. Please, I hope we have our calculators here. 9.8 meter per second square, because you're going to be helping us to calculate. All right, so look at this question. An object of weight 150 Newton um, moves with a speed of 4.5. So first of all, we take down all our parameters, okay? So the object, oh, this is meant to be take gravity, sorry. Let's just take gravity. So, so first of all, we follow it, all right? The weight of the object is equal to what? 150 Newton. Weight of the object is 150 Newton. The speed of the object, we can call it the speed or we can call it the velocity, it's 4.5 meter per second. 4.5 meter per second. And then the radius r is equal to 3 meters. Radius is equal to 3 meters. Right. So we're just going to relate this. Okay. So in order for us to get the mass from the weight, we know that weight is equal to mg or force is equal to mg. So weight is mg. Please take note of that. That weight is mass and gravity. Weight means weight changes, but mass doesn't. All right. So yeah, weight changes, but mass does not change. Right. So weight answers to the call of gravity, but mass wouldn't answer to the call of gravity. So it's small, weight changes to the call of gravity, but mass doesn't change. I'm wondering what we did in our physics class. I might just send it to make it easy. So now the mass here, we want to find the mass. So the mass is going to be the weight divided by our gravity. And that is 150 Newton divided by 9.8. You can approximate this to this. Okay. So 150 divided by 9.8, according to what is given to us in the question, that's our mental study. So 150 Newton divided by 9.8. All right, so that is going to give us 15.31. So I have my mass with 15.31 kilograms alone. So I've just gotten my mass. Now I can calculate my centrifugal force. The force that is keeping this operation along the circular path, I can calculate it. So I'll just say centripetal force. Please take note of the formulas, understand the formulas. Centripetal force Now it's going to be what? mv squared, remember? mv squared over r, mv squared over r, and then this is going to be mass, which is 15.31 times the velocity given to us is 4.5, so we say 4.5 square divided by, and what is our radius? Our radius is 3. All right, so, and we do that math. So I'm just going to do it here and calculate 5 square. All right, and that is going to give me 103.275. This will be the same. Okay. So this is just going to give me 103. 103.3. I can approximate this centimeter force to be 110 newtons, the nearest force. So that is that. Okay, so look at that properly. Do you have any questions on this? I need you to understand the concept first. Do you have any questions? If you're good, you can just give a thumbs up. Do you understand? All right. Okay. Try. Beautiful. All right. So let's check. Yeah, let's check another example. Let's see how we can clear this. Make this maybe clearer. Okay. Sorry about that. Okay. So let's say here now we say okay. Let's say if an object of mass 4 kilograms goes round. So goes down the center of 0.5 meters in 3.12 bar. Okay. What is the force towards the center? Okay. Let us understand circular motion and know the basics of circular motion before we move into simple motion. All right, so this one says a mass. First thing, if you would list out your parameters. So just that's the first thing. So in order for you to know the formula you're going to use, list out your parameters. Okay. So our mass is equal to 4 kilograms. Mass is 4 kilograms. Our radius is equal to 0.5 meters. And what else? Give us time, right? So our time is equal to 3.142 seconds. What I see here. So this one says time taken to go around the circle. Right? Time taken to go around the circle. Now the distance around a circle. Look at this. Remember, this is the circular motion we're dealing with here. So distance around a circle. If you're traveling around a circle like this, normally what we call it in maths then in our basic maths is called the circumference. The distance that travels around a particular shape is known to be the perimeter or the circumference. So this is going to be like the circumference of the circle. So before you start saying pi now, ask you, where did pi come from? So the circumference of the circle is always equal to 2 pi r. So we're familiar with that. So if you say the distance it takes, all right, if an object of mass 4 kilograms, since here an object of mass 4 kilograms goes round a circle, we just know that, okay, yes, this thing is traveling around the circle, and the distance around a circular path, which is circumference of the circle, is 2 by r. Okay. So now it's asking us for the force. So I'm going to say the time taken to go around the circle is time taken about t. So time taken to be equal to 3.142. And then we're going to into seconds. Then we can calculate, remember the formula for finding force. Centripetal force is equal to, that is the mass times velocity square divided by r. Okay, so now we have the mass, we have the radius, we don't have velocity, so we have to calculate velocity. You can remember the formula for velocity, did it in this class. So formula for velocity is equal to distance over time or displacement over time, whichever one, change in displacement with time over time. So now the formula for velocity is equal to change in displacement over time. What is the displacement? Displacement, like what is the distance that has been traveled around the object, or what is the circumference of the circle? The distance around the circle, like the circumference of the circle that has been let's travel around the object and all that. So we have that to be 2 pi. Okay. We're not going to include radius because radius is already existing here. So that displacement, so that distance around the circle, let me include the time first. So our time is 3.142. Let's know that we're including the right formulas. And then our displacement is going to be 2 pi. You can press 2 pi on the calculator, or you can press, yeah. So just give us the value. Someone should help us punch 2 pi. Just punch it on your calculator, give us the value of 2 pi. You'll see pi in where you see close to answer and equal to, you see the pi, you use sheep like pi. Where you see times 10 x
6.284.
0.284. Thank you.
6.284.
All right. Thank you very much, Samuel. So that is 6.284. Can we divide it 6.284? Can you divide it by 284, right? Okay, so don't divide it by 3.142. Divide it by 3.142.
That will give us 2.
So that is going to give us 2. All right. So now that is giving us 2 meters per second. So that is our velocity. So now we have our velocity. We just come here and impute our velocity. Now we found velocity. Remember, velocity is displacement over time. We found that using circular motion. So we just say 4 times 2 squared, which is the velocity, divided by 0.5. And this is going to give us, that's going to be 16, um, 16 divided by half, which is 32, right? So we have 32 newtons. Remember, it's force for looking for, so it's measured in newtons, right? So that's how we roll with it. Let us treat something under something that has to do with, let's say, radians per second, like an angular velocity, radius per second, because we need to know how to relate. Okay. Yes, Chidebere.
Okay, thank you. So, it's still not clear why we excluded the radius from when we were calculating the circumference instead of 2
Okay.
pi r. Right.
Yes. The thing is, if we use the 2 pi r here when calculating the displacement, in physics, when you want to just calculate the distance around a circular path, it's mainly 2 pi. You just use the 2 pi. The reason is because we're already including radius in one of the formulas that we're going to use, which is the centripetal force, or it could be the acceleration. So whichever one that's going to involve the radius, if we include the 2 pi radius here, and we still come here and divide it, we're going to be having a different value. So what they do in physics, since it's involving circular path and you already know your radius, or radius has been given, your displacement is 2 pi around the circular path, because it will affect
Okay.
your calculations.
Okay, thank you. Understand.
Right. Yes, all yours. Oh, all yours. Okay. I think that was eight. I don't know if you're speaking, but we can't hear you. Okay. Let's move on. When you can speak, just let us know. So, all right. So, yeah. Yes. Let us deal with something now that involves angular velocity because we're going to be using a lot of angular velocity. Now, there's something I want us to understand. Angular velocity now is this. You see, when this object was being, um, you know, this object is being accelerated through this, or there is a centripetal acceleration, it subtends an arc. It subtends an angle at the center. That's what it does. It subtends an angle at the center. Okay, this particular object. This angle that it subtends, this particular angle here, is what we call our angular velocity, right? So there is an angle that this object traveled round. It's traveling through a circular path. As it's traveling through a circular path, there's an angle it's going to subtend, which is this one. Now, the thing is, the angle is our angular velocity. Sometimes it is represented like this. So we have our angular velocity, then we can then say, okay, the angle that turns through is our angular velocity. So instead of beta, we just write that. Now, if we want to relate um, the angular velocity, okay, let's say this. Theta is the angular velocity, which is that, then this is actually measured in radians per second, just in case you see questions and you're seeing radians per second, know that that belongs to our angular velocity, right? It's measured in radians per second. The other things I need to let you know. Yes, there's a relationship between velocity, that is angular velocity, right? Is related to our normal linear velocity. So velocity is equal to, we multiply the angular velocity by the radius. Okay, so we can impute it. You can please take note of the formulas that linear velocity is equal to the angular velocity times the radius. But we might be applying it when, as we progress, we'll be applying these formulas. So if you're taking note of that, let's get on. Um, let's get on with this. So let's take, for instance, that we have. See, look at this. This one is going to involve son of mass 500 grams times a rope 50 centimeters long is well at an angular velocity of 0.0 rads per second. So, see, this is radians per second now. We already know that is for angular velocity. So this is calculated percent. Yes. Okay. It says calculate the centripetal force. Thought someone's done it. It says calculate the centripetal force that we have here. So it's sort of mass 500 grams. Now, the mass is in 500 grams. First thing we need to understand, let us list our parameters. First thing first in physics. Okay, list your parameters so you know what you're doing. You know what you're going to apply. So this is 500 grams, okay, which will sit onto uh, the normal unit, which is kilogram. Then we have our rope to be 50 centimeters. Okay, they gave us a measurement as 50 centimeters. Now, remember, it is tied to a rope. So that rope actually is the radius. So let me just explain this. Let's say we have something like this. Okay. Okay. Let's say we have something like this. And now look at, it says the stone of about 500 tons. So let this be the stone. We have a stone here. And then let's say you're the one standing at the middle here. The one standing at the middle. And okay, the stone is tied to your rope. This is your rope here. And then you start to what? Turn the stone around, like you're turning it around. So that means this stone is traveling through an angular path. Okay. So there's going to be angular velocity, right? There's an angle turn through that ellipse path, right? For that circular path, and which is given to us as 500. So the mass of the stone here, we have the mass of the stone here to be what? 500. This is the mass of the stone. Now this is your rope, which is also to be the radius in that circular path, and you're the one, spinning it. So it's going at an angular velocity of 12 radians per second as it travels through with time. So now it says we should calculate the centripetal force. So that means we have our radius to be 50 centimeters. We're going to change that as well. It's meant to be in meters. So all these units, just ensure that you can change your units properly. So the mass, we change 500 grams to mass. It takes 1,000 grams to make the kilogram. So to change from gram to kilogram, you divide by 1,000. So this is going to be, let's change it to kilogram. This is going to be 500 divided by 1,000 kilograms, so that we can get it in kilogram, right? So that is equal to 0.5 kilograms. Then for our radius, which is 50 centimeters, we to change it takes 100 centimeters to make 1 meter. So to change from centimeter to meter, you have to divide by 100. So this is 50 divided by 100, and which is equal to 0.5 meters. So let me just sorry about that. It's a bit of it. Sorry about that. I think that was a little glitch or something. So let me just put this here. This will be 0.5 meters. Now I'm going to state it clearly. 1,000 grams. These are your units of conversion equals 1 kilogram. 100 centimeter equals 1 meter. All right. 100 centimeter equals 1 meter. So we have 0.5 meters. We have 0.5 kilogram. Okay. Now we've changed that. We have our angular velocity. Our angular velocity is equal to 12. We got 12 radians per second. Radians per second. And then what else? It's asking us to calculate our centripetal force. So, and we know centripetal force. We write down the formula is equal to mv squared over r, right? So that is centripetal force, mv squared over r. So we just come here and we impute. Now let's find velocity. Remember, velocity is equal to what? Velocity can be related to our angular velocity. All right. So our linear velocity is equal to angular velocity times radius. So let us find the velocity first that this thing is traveling with this stone. So we're going to have 12 times 0.5. All right. And what's that going to give us? That's going to give us 6, right? Okay. So now we come here and we say our centripetal force. We're going to have what? 0.5 times what? 0.5 times 6 square divided by 0.5. And what's that going to give us? What's going to be the answer to that?
30.
Okay. Is it 30 or 36?
I'm getting 36 Newton.
Yeah,
That's 36.
36. Okay. So that is 36 Newton. Remember, let us remember to please impute the right values. Now, calculators. So 0.5. Yeah, so it is 36. All right. For those of us that have our calculators to be hanging, please go and return it back to the vendor. You cannot be using this kind of, because my calculator sometimes will just freeze. What's the meaning of this? Okay, yeah. Anyways, we'll calculate it the other way. 36. So this is how it is related. All right. So now that you understand the dynamics of this, we'll be moving into simple harmonic motion. So before we move into simple harmonic motion, I want us to do something, just to test our, just to test us something quite good, something quite easy. 1 second. Mm, is there any other thing that I've not explained? I'm trying to explain any other thing. Trying to see if I've touched every part here before we move to simple harmonic motion. The main. Okay. What other thing in angular velocity? Okay. So I told you that the angular velocity is represented as this radians per second. So this is the relationship between linear velocity and angular velocity, right? And I also said that the angular velocity is the angle turned through within an elapsed time when the stone or when the object is traveling around the circular path. So the object traveling around the circular path. So let's say this is a distance. Let me touch this. So the circumference of the circle, that's going to be it's 2 pi r, but in physics we're going to put it as 2 pi when we're calculating the distance, right? So it's 2 pi r, and that's the circumference of the circle. And then what else? Remember that 2 pi radians is equal to 360 degrees. Please, you can take this down, or you can note it down somewhere. 2 pi, we call it radians, meaning that is also equivalent to an object traveling around a circle, right? Giving an angle. So 2 pi radians is equal to 360 degrees. All right. And then what else? What else have we not done? Also, you should know that your angle or your theta, okay, your angular velocity itself, right, is equal to theta over time. That means the angle turned through divided by the elapsed time it takes to turn through that path, just in case you're giving time as well. So please take note of it, because we'll be applying most of this understanding of circular motion. We'll be applying it in simple harmonic motion. We'll be going into simple harmonic motion and all that. And simple harmonic motion is more of what they ask in our practical physics. But first, you need to understand circular motion. In simple harmonic motion, you find the simple pendulum. So we'll progress into that. So before we move on, do we have any questions? Or do we want to go and grab something to eat fast? Or we're still good? So check this out. Any questions? Any questions?
But
Yes.
that formula you wrote down, is it 2 pi r is equal to 360?
Oh, 2 pi radians is just 2 pi, but most times they call it the 2 pi radians, because like that's one of its units. I'll
Uh,
zoom out of the diagram. All right. So that's all right,
Yeah,
Ibrahim.
excuse me. Sorry,
Yeah.
I just joined now, and it's like just a drama to me. Can you please explain over again so that I can be able to follow up, please?
What part do you need me to explain?
From that theta something.
Okay.
From that,
First of all,
yeah, yeah,
so do you understand all what we've done here? Like
yeah.
these questions.
The question I didn't because I just log into right now.
Uh, okay. All right. So I'll just brush through it quick. Okay. So
All
this
right.
is, yeah. Now, let's say we have you at the middle here, standing here, and then you have an object that travels through this path. The first thing we talked about was the centripetal acceleration. And the centripetal acceleration is, okay, before I explain before I explain all this to you, I just wanted to give um, a brain teaser question. One second, I'm going to explain it. Let me just give a brain teaser question to the class first. Yes, while I explain that, let's see if you guys have this clear understanding and you can do this. Apply any of the formulas that have been given to you. Remember that diameter in circle is equal to radius over 2. So 1 revolution per second, calculate the velocity of the wheel. Okay, just a brain teaser. We have a radius. The radius have to be the diameter divided by 2. That's how we do it. And they said per second. So that means our time is 1 second. They also gave us, they said 1 revolution. And 1 revolution is 360 degrees, which is 2 pi radians. Okay, so apply. And let's see. All right, so back to you. So yes, I was explaining that if, let's say this is you here at the middle, and then you tie a rope, okay, and with a stone or a biro or pen, and then you're flinging it around, okay. Now there is an acceleration, okay. There is an acceleration that is keeping that object or that stone that you tie, and let's say you use a rubber band and then you're just spinning around, okay. There is an acceleration that is experienced by that stone undergoing circular motion, and it is directed towards the center of the circular path, which is you that you're spinning it, right? That is what we call the centripetal acceleration, which is v squared over r. Now acceleration, change in velocity, okay. All right, so that is acceleration, change in velocity over time. So in centripetal acceleration, instead, it's going to be v squared over r. This is how we calculate the centripetal acceleration. Now there's an angle turned through when you're spinning, right? It's going to give you an angle. That angle, okay, is what we call that angle is related to what we call the angular velocity, which is this here. There's always an angle that is elapsed, all right, and it travels through a distance in the circle. Like you now, you're spinning that stone round, so that's a circular path, right? And you know that in mathematics, the circumference of a circle is 2 pi r. In physics, we just say the distance around the circle is 2 pi, all right? And 2 pi means 360 degrees. 360 degrees means 1 revolution. 1 revolution means it completes one round. It goes 1 round, like you spin it. It has gone like this and it has come back. So that is like 360 degrees. All right. So when we're relating, we can say that the theta is equal to the angular velocity. When we want to relate the velocity to angular velocity, we use this formula, but let me not jump into that. I was in centripetal acceleration, right? So now that you're spinning that object, there is also a force that is pushing the object or making the object to rotate around the circular path. This is what we call the centripetal force. Now, we know that normal formula, the force is equal to mass times acceleration. So centripetal force is going to be equal to mass times centripetal acceleration, not just normal linear acceleration, right? Because now we're dealing with a circular path or something in circular motion. So this is going to be mass times velocity squared over r. That's v squared over r. And that's going to be mv squared over r. So if you bring down all the formulas, you have this mv squared over r. Now, okay, we then started treating questions. We said an object of weight 150 newtons move with a speed of 4.5 meter per second square in a circular path of radius 3 meters. Calculate a centripetal acceleration and the magnitude of the centripetal force. Take gravity to be 9.8 meter per second square. Now we have the weight in physics. First of all, just list out your parameters so you don't get confused. You know exactly what you're doing when you list out all your parameters. So you just know, oh, this is what I'm doing, this is what I'm doing. Now the weight is equal to 150 newtons. The velocity is 4.5 meter per second. And we have the radius to be 3 meters. Now weight changes, mass does not change, meaning that a baby can grow because it answers to the call of gravity, which is G. but mass stays the same. Mass is constant. All right. So weight is equal to mass times gravity. And then we find mass by just dividing, making M subject formula. We divide both sides by G. Yeah, so that we can be able to find our mass. So mass can now stand on its own. Okay. So that's how we got that part there. So, and then we found the mass after dividing. Then centripetal force is going to give us what? Mass times velocity square over r, which is our velocity has been given to us as 4.5. So we just imputed the formula and we got this. That's 103.3, which is approximately 103 Newton. That's how we did the first question. Do you understand
About
that?
9.8 there.
Yeah, 9.8
Under
meters per
that
second.
150 Newton
That
divided
is
by
our gravity.
9.8. Okay, okay. All right.
Yeah, to get our mass.
All right. Oh, got it.
Okay, so now in the second question here, it says if an object of mass 4 kilogram goes round a circle of radius 0.5 meters in 3.142 seconds, it says what is the force towards the center? All right, so now we're just still looking for centripetal force. So we have mass equals 4 kilogram and the radius is 0.5 meters, and the time, they give us a time to be what? 3.142 seconds. Now, in this question, we don't have the velocity. We come to our linear velocity. We understand that velocity is equal to displacement over time. That's the normal linear velocity, like changing,
Yeah.
yeah, just like you calculating speed. And now we said that the displacement, because it goes round a circle, so the displacement, that is the distance of a circle, is 2 pi. Like I said here, when we're calculating the distance of a circle, we use 2 pi r in mathematics, but in physics, we just say it is 2 pi, meaning it is going round the circle. Okay. So that's like we use that to calculate the distance round the circle. So we just related that here. The velocity
Okay.
equals 2 pi over the time they gave to us is
Yeah.
3.142. So we divided that
Okay.
and we got 2 meters per second. Then we just imputed it into the formula, which is mass times velocity square over 0.5, and we got 32 newtons.
Mm, okay.
Do you understand that?
Mm,
All right, so now check this one out. It says a stone of mass 500 grams tied to a rope 50 centimeter long is whirled at an angular velocity of 12.0 radian per second. Now, I also said that there's a relationship between velocity and angular velocity. V, which is the linear velocity, is equal to angular velocity times the radius. This is the relationship between them. It's a formula you need to like take note of before we dive into. In fact, all these formulas you need it before we dive into the main simple harmonic motion. Okay, this was just to clear understanding that aspect. Okay, so now, mm, 1 second. So now, our mass, we have to change it to kilogram. So this is 500 grams. To change grams to kilogram, we have to divide by 1,000. And this is centimeters. To change centimeters to meter, we have to divide by 100. So these are the units of conversion. I wrote them down. So just so we
mm,
can take note of it. 1,000 grams equals 1 kilogram. You know, we used to sing that in school those days.
yeah.
100 centimeters equals that's boring stuff.
Yeah.
So now we have the
Mm,
radius to be 0.5 meters and we have the mass to be 0.5 kilogram. And our
okay.
angular velocity is 12 radian per second, according to what they've given to us. They're asking for centripetal force. We know the formula of centripetal force to be mass times velocity square over r. Okay, but first of all, we need to find velocity since we're not given velocity. So we just use our angular velocity times r. This is the relationship. So we can just use this angular velocity and this radius to get our velocity, our linear velocity. So we multiplied that and we got 6. 12 times 0.5 after we convert it. So we're using the basic units, kilogram and this in meters. 12 times 0.5 and we got 6. So we just imputed the 6 in this formula and we have 36 newtons after we calculated. So I went further to explain that that the distance around the circle, or when you're going around the circle, it is 2 pi, and 2 pi is also equals to 360 degrees, and 360 degrees means one revolution, and one revolution means when you're going around the circle. So it's just like you going a distance around the circle. I also said that the angular velocity is equal to the angle turned divided by the ellipse time. That's per time it takes to go round. So that is angular velocity related to degrees. Okay, and then I give a brain teaser question at this part here. I said if a wheel, so guys, have we solved this? If a wheel 1.2 meter in diameter, remember that in circles, diameter is equal to 2 radii, meaning that radius is diameter over 2. So you have to divide the diameter by 2 to get your radius. All right. So if a wheel 1.2 meters in diameter rotates at 1 revolution per second, 1 revolution per second. It says calculate the velocity of the wheel. We know what one revolution is. One revolution is 2 pi, or yeah, is 2 pi. And you just use your calculator for 2 pi. So we can calculate our angular velocity using this. So let's bring out what we have. We have our diameter to be 1.2. They also give us 1 revolution. So they gave us 1 rev. Please, that is 1 rev. Okay, they give us 1 revolution, and they won't tell you what 1 revolution is. So you just know it is 2 pi. In cases where they give you angle, you know that this one is 360 degrees. Okay, but they didn't give us any angle here, so we just leave it as 2 pi. And then they said it rotates at 1 revolution per second. So that means per 1 second. Our time is what? 1 second. It says calculate the velocity of the wheel. So it wants us to calculate the velocity of the wheel. And first of all, yeah, so it wants us to calculate the velocity of the wheel. So what this is giving to us here is our angular velocity. Remember that angular velocity is equal to what? Theta over time, right? Theta over time. And this angle is also equal to what? 2 pi. So we have 2 pi over time as our angular velocity. So we have our angular velocity because we have a revolution, we have seconds. So already we're having angular velocity. It wants us to calculate the velocity of the wheel. And the relationship in linear velocity and angular velocity is what? Angular velocity times the radius. So let's find radius. Radius is going to be equal to what? Diameter over 2. So we divide this by 2. And when we divide 1.2 by 2, what do we have? We have 0.6, right? So this is going to give us 0.6. And we just come here. Okay, so 2 pi over 1 is still, yeah, someone help us. Okay, yeah, you said it's 6.28, right? Or what was that value you gave to us again?
6.284.
Okay, all right, thank you. So 6.284. Then, so that means we divided by 1 is still the same thing. So over 1 is still the same. So we already have our angular velocity. So we just come here to find our normal velocity. So this is 6.284 times our radius. And what is our radius? 0.6. 0.6. All right, so you can help us calculate that.
2 pi is 6.283.
Oh, is it 2.6.2? You know what? Let's let's keep it at 2 decimal. Okay, let's just leave it at 2 decimal. So now approximately you're correct, Abby. So let's multiply by 0.6. So let's find our radius. If you use 283 and 284, we're still going to get approximately the same answer.
That is 3.768.
Okay, 3.768. If we're going to if we're going to approximate this, So that's going to give us what? Let's say to the nearest um, to one decimal, that would just be 3.8 meter per second. So depending on your answer, if your answer is two decimal, if your answer is one decimal, on the options that are given to you. So we have our velocity to be that. Any questions? Okay, so we're good, right? So we sure we're good. We have a clear understanding of circular motion. This is just a brief um, answer 864 newtons. What? Which of the answers? Is it this question or there's another one? Okay, okay. Maybe that's not for this question. All right. So if there are no further questions, let us move to the big boy, which is simple harmonic motion. So thumbs up if you grab the concept of circular motion. All right, fantastic. So if you don't have your thumbs up, it means you're still having a little bit of problems, right? You can ask your questions now before we move further. Okay, no questions. It's a moving train and we're moving into the simple harmonic motion now. So let us deal with this guy. Let's deal with him. Simple harmonic motion. So the body is said to undergo simple harmonic motion in two cases. Case number one, its acceleration is always directed towards a fixed point, just like you have in a centripetal acceleration. And then its acceleration is directly proportional to its distance from its point. So I'm gonna write that down. Don't worry. I'm going to write that down. So um, okay, so if its acceleration is always directed towards a fixed point, its acceleration is directly proportional to its distance from the point. All right, so let's get it. Now, the first thing we want to understand is um, the period. Okay, the period of a simple harmonic motion. Period actually means the time taken to complete one cycle, oscillation, or vibration. You do this in waves. Luckily enough, we're not doing waves. So we need to understand period. Period, like I said, is the time taken, that's a capital T, to complete one revolution. So it's time taken to complete a number of um, revolution. Time taken to complete one revolution. All right. Don't mind my handwriting, be cool. Like we're all on that time and pressure here. So it is time over n. That is what period is. I will be dropping down formulas because we're going to need those formulas while solving things under the simple harmonic motion and also getting into simple pendulum. We'll, we're going to be needing those formulas. Okay, so um, now we have the period to be that. Then we also have another thing called frequency. You see, period and frequency, they go hand in hand because they are almost like brothers. It's just that they're opposite to each other. One is time taking. The other one is just, the number of oscillation per time. So it's like the exchange. So frequency is the number of complete oscillation per second. So the number of oscillation per time it takes. So both of them are just different. Now the period, let's have this here. So the period is this. I have this, and then I have this. And then I have this. So let's say the time it would take to move or complete round this or complete this revolution or the number of revolutions. This is like just saying like one revolution or one round. All right. The time it will take to complete the one round is our period, which is T. That's the period. Now, the number of rounds per the time taken is our frequency, F. So how fast can this thing go round this circle? Can we travel? Can this stone, this object travel around? Let's say this is the object. How fast can the object travel around the circle? In how many seconds? That is what the frequency is doing. So frequency most times, period most times is measured in per second. So we can just say it is second, right? You can just call it second. And then, sorry, this is measured in seconds because it's talking about time. Well, frequency, this one now it is per second because this is over time. So it is frequency that is per second, or you call it hertz. I'm sure on our phones we do see that a lot. We see the hertz. It means how many or how fast while our phone is carrying one operation or our system is carrying one complete operation in how many seconds. That's what the hertz is telling us. What is the number of oscillations or what's the number of vibrations the phone can carry or the system can carry in a second? That's what frequency is. So hertz. Okay. So now we can then apply these formulas. I told you that simple harmonic motion has close to like relatable 11 formulas. If all the formulas are relatable, all right, it has close to relatable 11 formulas. Now, we also have what we call our amplitude. Just before I go into that, we have what we call the amplitude. The amplitude in, okay, we also do this in waves, but luckily enough, fortunately for us, we're not dealing with waves. So let's say we have this. Amplitude actually means like the maximum displacement, okay, from the central or equilibrium position of that body. So let's say I have, if it's wave I'm dealing with now, I usually used to explain this very well in wave class. So let's say this is wave now. From this point here, the equilibrium point, to here. It's the maximum displacement. That is what the amplitude is. Now, for our circular motion, this is our equilibrium position to the maximum place it gets, all right, or it can stretch further. So this becomes our amplitude, all right? The maximum displacement of a body from its central or equilibrium position. That is what the amplitude is. Displacement of the body. Now, we can then say, so this is just like displacement. We'll be dealing with a lot of problems on the amplitude and all that. We can then say that these formulas are relatable. Maximum displacement. Now, let us check the formulas. We know that angular velocity is equals to the angle turned or the time it takes. One, we know that velocity is relatable to angular velocity times radius. Now, we can call this the radius, which is also like an amplitude, right? The displacement from the equilibrium to the part of the circumference. So we can call this radius, or we can say angular velocity times amplitude, whichever one they give to us, we calculate it. So now you have a clear understanding that radius can also mean the amplitude when going into the simple harmonic motion. Now, we can also relate this angular velocity to the frequency. There's a formula it relates to frequency. You know that angular velocity is look at angular velocity, the angle turned through over the time taken. And that is just like frequency, right? An angle turned through can also be 2 pi over the time taken. So angle turned through over time taken is just f, frequency, right? Number of oscillation over time, that is frequency. So we can say angular velocity equals what? 2 pi f. We can, so that is 3. We can as well say that our period is equal to 2 pi, okay, over the angular velocity. All right, so if frequency is equal to, remember, frequency and period are just like brothers and sisters. It's just that, or brothers, it's just that they're opposite to each other. So now period is t over n. And then frequency is what? N over t. So I can as well say period is equal to 1 over frequency. So if I have frequency itself to be equal to, if I make frequency here subject formula, it becomes 2 pi over angular velocity. So that means it becomes angular velocity over, when I divide both sides by angular velocity, I was calculating period. So it becomes angular velocity over 2 pi. Now, the opposite of that is going to be period, right? So period is going to be the opposite. That is 2 pi over angular velocity. So they are relatable. So we have 4 formulas down. Before we start moving into the next formula, any questions?
Yes, please. I got lost when you were calculating the angular velocity. The one you said angular velocity is equal to 2 pi times frequency. I'm confused on how you got your t, that's your period, equals to 2 pi all over angular velocity. I didn't get that part.
Oh, okay. All right. So you know that period and frequency are opposite. This is period, right? And this is frequency, meaning that period is 1 over f. That's the flip of f, right? So now, from this part here, if I divide both sides by 2 pi, I'm going to have angular velocity over 2 pi. And then I know that my period is 1 over f, right? That's the flip of 1 over f, which means I'm just going to flip this one as 2 pi over angular velocity. Or if I want to divide this, I say, let's bring this down. Let's break it down. 1 divided by f, right? F is angular velocity over 2 pi. Using keep change flip, I just divide the fraction. To divide a fraction, you flip the sign and change to multiplication sign. So that is 2 pi over angular velocity. That's how we divide fractions. And so we have 2 pi over angular velocity. So this is the mathematical breakdown, the normal basic maths breakdown of how that formula came about, because we're flipping the frequency, okay? Because they are both hand in hand. So frequency is also going to be 1 over period. That's how they work. Okay. Do you understand now? All right. Good. Now we have 4 formulas down. Are all these with us? Like, are we good to go? Let's get to the next formula. The next formula is going to be our acceleration. You see that acceleration that we have? Acceleration now, we're relating acceleration to our angular velocity. Our acceleration is going to be angular velocity square multiplied by r. This is a relationship between acceleration and angular velocity. So let's see how we talked about this. So velocity normally is just angular velocity times r as the relationship. Acceleration is square of the angular velocity times r, because it's a change in velocity in respect to time, or with a radius in circular motion. So it's going to be double of that of, it's going to be the square of the angular velocity when related to normal linear velocity. We can say this is r, or we can say angular velocity square times a, whichever one we like. So we can call it that as well. Okay. So that is number 5. Number 6 is that our acceleration, okay, so I talked about the angular velocity. Then we also have what we call our angular acceleration. Okay, we have what we call the angular acceleration. Okay, so you can also use this formula to solve angular acceleration, just in case you're asked.
Sorry, please. How did you come about the acceleration is a equals to angular velocity over squared out. Then how do you come about the angular velocity of capital A? So I'm lost there.
Okay, so remember I told you that amplitude is also displacement, and amplitude can also mean, this is also representing r, radius. So if we have r, we can have a. They can also put it as amplitude. Yeah, so just the r that can also be replaced as a. They're all in meters.
Okay.
Okay, so all right. So okay, let me relate this other formula. I said that frequency is period is this. So let's relate frequency. Frequency is also going to be, frequency will be what? Angular velocity over 2 pi. Okay, so that is, how many have we got? 1, 2, 3, 4, 5, 6. All right, 6 now. Now we know that we know theta is equal to 2 pi. All right, we call it 2 pi radians, which is also equal to 360 degrees, which is also equal to our 1 revolution, or you call it 1 round. Okay. So how many now? 7. We established that. Then there's another thing you also need to know, that when you're giving the frequency, you just say that the period, we've already established this, is 1 over f, 8. When you're giving the period and you want to look for the frequency, we say that the frequency will be 1 over t, 9. What else do we need to know? Now, there's also another relationship between when calculating angular velocity. All right, when calculating angular velocity and we have distance. Let's say we have from here to here now is our amplitude. Then we're asked to calculate it at a particular distance here. Let's call this one x. Let's call this another x, another distance at this part here. So we have our normal radius and we're asked to calculate it at this point. So we can relate our angular velocity. Right? We can relate our linear velocity to be equal to, our linear velocity is the normal angular velocity. Instead of having radius now, where you lost the Brian.
Sorry, I'm totally lost starting from where you started looking for the formulas for this angular velocity, the acceleration.
Okay, you mean at this
Yeah.
part here, when we started the formulas.
Yes, exactly.
Okay, you know, some of the formulas, we've already established it in our circular motion. So we're just applying it here. First of all, we talked about
Okay.
period. And I said period is like the time it takes to complete one round or one oscillation, which is measured in seconds. Then we now said frequency. That okay, for the frequency is how many rounds can we complete in a second? That is what frequency is. That is hertz. Or how many vibrations, or how many oscillations, or how many revolutions can we complete in 1 second? That is frequency. And we have n over t. And I said that okay, period and frequency are like brothers. It's just that they are opposite. One is period, one is in second, one is in second. All right. So if this is t over n, this is n over t. We can just relate it as 1 over f.
So how can I apply my discipline?
So related as hot mic,
I want to apply this.
Is it on?
hot mic.
Someone should practice and should,
Okay, let me just mute. Okay, all right. So we have the period to be 1 over f and frequency to be 1 over t because they're just like opposites. Okay,
Yeah.
so come down here and we said our amplitude is like the radius. So sometimes they'll give you the amplitude in meters or they give you the radius in meters. So come down here and we say that the angular velocity is equal to theta over time. All right, we've established that in our equations before. And then we also know that velocity is equal to angular velocity times our radius, or angular velocity times amplitude. We've done that in the previous one. Now, we also say that angular velocity is 2 pi f. That means the theta, since this is angle turned through over time taken, so that is a revolution or n, number of oscillation over time. We just say that angular velocity is 2 pi f. That's frequency, since it's relatable. Okay? And then we say, if we make f subject formula here, we're going to have
angular velocity.
velocity over 2 pi. And if we understand that period is the opposite of angular velocity, which is 1 over, so we just flip it. We use 1 to divide it, and that's giving us 2 pi over angular velocity at this part here. Okay, so that's what we applied here as period. So period is equal to 2 pi over angular velocity, while frequency is angular velocity over 2 pi. Then we also established that our angular acceleration is equal to angular velocity square times our radius. The radius can also be the amplitude, so they can switch it or tell you it's still the same. All right.
Okay.
Amplitude is maximum displacement from the center of the circle. They call it the equilibrium point. Okay. And then we also established that theta is equal to 2 pi, and 2 pi is equal to 360 degrees, and 360 degrees equals to one revolution, or we call it one round.
Mm.
Okay. Then we also know this one. Period is 1 over f, and f is 1 over t, 1 over period. That's frequency.
Okay.
So we're at the 10th formula now. I think this is where we'll just draw the curtain, where we said that if we have if we have the amplitude and we have x, like let's say they ask us to calculate it at this distance here,
Mm.
at this point here. So what we're going to do is from this point to this point at here, how we're going to calculate that. So that is going to be, we're going to find it like using Pythagoras theorem. It's going to be like the amplitude square. Okay, so we'll have the angular velocity first of all, then we'll have the amplitude square minus the x, the other distance that they're asking us to solve, or they're asking us to find. So these are like the main formulas. Oh, we also have as angular acceleration equals to, one second. Okay, let me put it here. We also have angular acceleration equals to um, our a times our radius. So it's just like these formulas, both of them here are relatable. Okay, so if you can get your angular acceleration here, you can still come and put it here, just multiplied by the radius. So it's still relatable, still almost the same thing. So these are just like the 11 main formulas that are applicable in simple harmonic motion. Problem now is, where do we apply
On how to memorize all this one.
it? Well, at least you know that I know that we can boast that 1, 2, 3, 4, 5, 6, 7, 8 is something that can stay in our head because we've done it in circular motion. We've related all these ones in circular motion, and period and frequency, we can easily relate them. So those 8 can stay. The remaining 3, we'll find a way around it. So we need to understand that aspect before we jump into the um, simple pendulum and energy of simple harmonic motion. So yes, let us see how we're going to apply this. Let's take some examples. Let's take some questions. Don't worry, if you guys can understand the concept here, you'll have no problem. Let's familiarize ourselves a little bit with the example, just because of time. So we'll see how we can apply these formulas, and then we know, okay, yes, this is something we're all going to pass. Let me see. All right, so let's take this with a constant speed. Of, let's say, 8 meter per second. Calculate the angular velocity of the object. Let me just drop down. Let me drop down some questions. Okay. All right, so let's say this is 4 pi. Uh, where do I impute that guy? Sorry, 1 second, please. So, okay, so let this one be wow, funny enough, I don't see it in my windows. All right, so that one just be 4 pi. I'm just going to write pi there. It's wasting my time for the unit to come out. I'll put it there. So let it be 4 pi and 4 pi seconds, rather. The amplitude of oscillation is 3 meters. Calculate the maximum speed of the particle. All right, so let's just do like 3 or 4 so that we know that we really touch this. All right, take another one here. Okay, so let's say we have a body is rotating in a horizontal circle radius 2.5 meters with an angular speed 5 radians per second. Calculate the magnitude of the radial acceleration of the body. Okay. Let's see. A particle moves in a circular orbit of radius 0.02 meters. The speed of the particle is 0.88 meter per second. Calculate its frequency. Yeah, in cycles per second. All right, just 4 easy you know stops, and you're just going to determine which of them we're going to use. All right, so here we're going to list our parameter. The first question says an object of mass 0.4 kilogram. So we have to be equal to m to be equal to 0.4 kilogram. What else are we given? What other parameter? Oh, it says radius is 2, so we have radius to be 2 meters. What else? What else? We have a velocity. That's the speed. The velocity is 8 meters per second. What else? What else are we given? We're asked to find the angular velocity. Okay. So, oh, sorry, that's going to be omega. So that is this, right? The angular velocity equals to this, right? So we don't have that. All right, so that's what we're given. So guys, which formulas do we use to solve this one?
My best guess, angular velocity equals to 2 pi over frequency. 2 pi a ten f.
Okay, so if we use that formula with this one that we were given, what about the angular velocity? Remember, the angular velocity has been given to us, and velocity has also been given to us. We're asked to find that angular velocity rather. So we know we have velocity, right? And this is omega r, right? So that means our angular velocity will be equals to divide both sides by r. That'll be v over r, right? What do you think?
Exactly. Yeah.
So this will be 8 over our r is 2, right? So we can
That's
relate this
4.
formula here. Where is it? This one. We also use it in circular motion, remember? We use it in normal circular motion. So something that is applicable. So that is 4 meter, 4 radians per second, because this is radians per second. So that is 4 radians per second. Okay. So let's see this one. They said the period of a particle is 4 pi seconds. Oh, this is meant to be pi. I was looking for that pi. So it's 4 pi seconds. So our period t is equal to 4 pi seconds. Mm. Then what else? They said the amplitude. So we have A. Amplitude is equal to 3 meters. Just also calculate the maximum speed. Also calculate V.
Please, sorry, I got lost. I'm trying to figure something out, right? The first example you gave, we are looking for the angular velocity. And from the formula that you dropped, unless I'm wrong, angular velocity is equals to v is equals to angular velocity square r. Is that not it? Well, I can't see the square. Or are we not applying it?
We're using this one. Since we already have the velocity and
Okay.
radius, we just relate it. That's what we did in circular motion here. We just use what we have, and we relate it. Let's look at
So
it. We
we are
also did
throwing
it.
away the mass of
We don't need the mass.
the mass of the item. We are throwing it away.
I'm not trying to. We don't just need it in this formula. We don't need it.
Some question will carry problem.
Yeah,
Okay.
some questions we just carry extra serenity to come and confuse us. Well, actually, since we know the formula we're using, mass is not involved, so the mass should go and sit down first. This is what we are asked to find, and we'll find what we need. This, and it's not relatable to the mass as of. We don't need the mass as of that time. The mass is just there to shake you. So once you know your formulas here, once you know how to apply the formulas, at least if you have the understanding of the normal circular motion we did, then you already have like 6 points forward. Then plus the frequency and this thing, you have like 8 points forward with those formulas. So you just know how to relate all of them. Okay. So we have 4 pi seconds equals 3 meters, and then it wants us to find our velocity. Okay. Wants us to find velocity. Okay. And we know that velocity right now, velocity is equal to omega r, or we can say angular velocity times amplitude, right? You can either say radius or you can say amplitude, right?
Yeah.
Okay, so if we have that, so that means we need to find omega first. Do we have anything here we can use to find omega? We can use to find this angular velocity, this guy. Do you have anything we can use to find it?
Just the 4 pi.
Okay, yes. So we can relate that to our period. Period is 2 pi over our angular velocity. So if period is 2 pi over angular velocity, you can just say that since period is 2 pi, it's 2 pi over angular velocity. Okay, we can say angular velocity will be equal to what? That is equal to, let's make angular velocity subject of formula. What are we going to have? Making angular velocity subject of formula. What are we going to have?
Two pi over t.
2 pi over t. So we'll have 2 pi over t. Okay, so if I relate this properly, this will be 2 pi over, our t is 4 pi, over 4 pi. So this is just going to give us 1 over 2. And 1 over 2 is 0 0.5. We have 0 0.5 radians per second. 1 second. 0 0.5 rads per second. That's like our omega. We've gotten that angular velocity. So we just come here and apply it. Now V will be equal to 0 0.5 times 3. Amplitude is 3. So just apply it. So 0 0.5 times 3, that's going to give us 1.5. So we have 1.5 meter per second. And that's that part there. Any questions? Okay. All right. Good, good, good. Next is all right, sorry about that. One of us was calling. Instead of that I'm here. Like she didn't see the link or something. All right. Okay. So this one says a body is rotating in a horizontal circle of radius 2.5 meters with an angular speed of 5 radian per second. So our radius, we have radius of what, 2.5. What else do we have? Let's list our parameters. We have our angular speed, 1 second. So that's going to be our angular angular speed is also known to be angular velocity. So let's not be confused. So our angular velocity to be equal to what? So it's 5 radian per second. What else do we have? What are we? Okay, 5 rad per second. What else do we need to find? It wants us to find our acceleration, find the radial acceleration of the body. So which of the formulas are we going to use? Which of the formulas are we going to use?
We're going to use A equals to angular velocity times r.
Okay.
That is a equals to angular velocity then r.
Is it this one?
Yes, yeah, this
Acceleration.
one.
Okay. So we have our omega. So we're just going to apply A equal to angular square times r, and that is going to give us 5 square times 2.5. And yes, if we multiply that, what are we going to have?
Like 62.5.
Yeah, 62.5. That's correct. Okay, so we have 62.5. So 62.5 meter per second square. All right, let's check another one. It says a particle moves in a circular orbit of radius 0.02 meters if the speed of the particle is 0.88 meter per second square. Let's write our parameters. We have our radius to be 0.02. We have the speed of the particle, that is the velocity, to be 0.88. And it is asking us to calculate our frequency. So, so which of the formulas do we use? Asking us to calculate frequency. Which formulas do we use? Can we get our omega? Can we get anything from here? This is a formula for frequency, right? Omega over 2 pi.
Yeah.
Okay. So if we have that, we're gonna have omega over 2 pi. So let us find omega. We know that velocity equals omega r, and that's angular velocity times r. So to find this, we have to divide both sides. Hello?
Yeah, very.
The link is in the group. Are you in software engineering group? All the 3 groups, I posted it there this morning. Check, the link is there. Don't worry, I'll post it in your DM now. You join. I'll post it in your DM. Mm. Okay, sorry. Just a brief call. So, so we have sorry guys, 1 second, please. Let me just quickly paste this thing. One second, guys. Well, this girl just go and find the link. Okay, I've seen this link. Sorry, I just want to share my link. Okay. Okay. Yeah. So as I was saying, so this one is equals omega r. Let us find. So we divide both sides by r. So our omega will be v over r. So let's find that. and V over R, that's going to be 0.88 over 0.02. Someone should help us with that. Calculator is freezing. So omega will be equal to
That's 44.
44. Okay, so we have 44 radian per second. So we have 44 radian per second. We just come in and apply for the frequency. So that's going to be equal to 44 over 2 pi. So 2 pi is 6.38, right? If I'm correct. Yeah. Then
6.28.
oh, 28. Okay.
Yeah.
All right. So we come here and we calculate that. So 44 divided by 6.28. Let's see.
7.006.
Okay.
6.8.
We have 7.
6.81.
What is 6.8?
Yeah, 44 divided by 3 is 6 to 3. Okay.
No, 44 divided by
It's
6.28.
7.0. It's
Yeah, 7.0.
7.0.
Yeah. 7.0. Thank you. All right. So yeah, that is that. Any questions? I just wanted us to familiarize a little bit. Any questions on that? Okay, no questions. All right, so let's move on. All right, so let's move on. Let's go into the simple pendulum. Let's move into this. Now we have that understanding, so we can dive into this guy with full force. All right, so now this is almost like simple harmonic motion. This simple pendulum is almost like simple harmonic motion. So all the equations that we have can be applied. All equations we have in simple harmonic motion can be applied in this simple pendulum. So we're going to be having I'm going to be breaking down these formulas. Now, this is the period of a simple pendulum. I'm sure most of us have seen this before. You just have something like this, and there is a big ball. Okay, and then this ball, when you start hitting it, it can move in this direction and also come back to this direction and maintain its original state. So it can move like this, it can go and move like this and maintain its original state. So the motion of this ball or the pendulum bulb, all right, it can move like this to this part here and still come back to its equilibrium and move to this other side here. So that's the pendulum. So if it goes to and fro means it has gone from this part and traveled to this part. So if it goes to and fro, it means that what for to and fro, that is one complete revolution. All right, that is one complete revolution if it goes to and fro. So most times, remember then in school, practical physics, or when we're doing a physics practical, they ask us to tie the thread to the pendulum bulb. Then we just hit it, and we start we'll raise it to a particular amount, like a particular centimeter that will measure from the pendulum stand, and then we let the ball, let the pendulum bob roll. Then if you just keep on going, to and fro, to and fro, and then we'll be calculating to and fro one, to and fro two, to and fro three, and then we'll be calculating the time it takes until it gets to the normal distance. I don't know if we did that in our practical physics lab, but we always play with it then in school. So the period of a simple pendulum, that is t equals 2 pi. This is the formula for the period when it comes to simple pendulum. And I'll be telling you why they're using this formula. This is 2 pi root L over G. The reason is this. The length, the G, normally G is our gravity, because this is obeying the call to gravity, right? So everything here is going to be obeying the call to gravity, which is pulling it towards the center of the earth. Now, the L is actually the length of the thread, or the length of the pendulum. Okay, so that length of the pendulum, that's what the L is representing. And then we have our 2 pi. Okay, we have our 2 pi. So instead of us saying here that it is 2 pi over our angular velocity, we just say that it is 2 pi times the root of the length of the thread and in respect to gravity. Okay, so let me just write that down. L is the length of pendulum. This is length of pendulum. Length of pendulum. Then this is gravity. We already know, we're already familiarized with 2 pi. So this is gravity. All right, so now I'm saying that, okay, now let's say that we can compare this pendulum. Let's call this pendulum 1 of this pendulum. And let's say we have another bulb that is being tied to the pendulum, or another bulb connected at its own equilibrium. So let's say this one too spins. Okay. So it could be in the same pendulum. All right. Now the length of the pendulum is going to give us, is the main factor, or is like a difference or distinguishing factor between the first pendulum and the second pendulum. So just focus on the white and the red. One is longer than one. All right. So if we're going to be comparing two pendulums, because some questions will give us, okay, you have pendulum 1, and then for the second pendulum comes like this. We saw this kind of questions. So we have pendulum 1, and then the second pendulum comes like this. What is the frequency? What is the mean period of the pendulum? That is both pendulum combined. You can even have 3 pendulums and all that. So they'll be giving you the values and all. So let us calculate. Let us see what this means. So if I have a period, that's one period, and I have the length of one pendulum, and I compare it with the one in red, that's the period and the length of the other pendulum in red. Okay. All right. The length of the pendulum gives us the main distinguishing factor. Okay. So what I'm going to do is I'm going to ensure that I'm able to get get the length, and I'm able to get the gravity out of the equation. So this is what I do, and this is how I relate the equation. I'm going to ensure that the pi and the gravity goes out of the equation, so I can relate the length to the period, because this is what we're looking for, right? This is what we're talking about, the length of the pendulum 1, and this is length of pendulum 2. So let's say we have 2 connected together. So the formula becomes like this. So I want to just make sure that I'm having T over L, T in respect to L in my formulas, so that I can relate pendulum 1 and pendulum 2 in respect to the length of their thread or the length of the pendulum. So this is what I want to ensure that I get. So what I'm going to do here is a formula though, but to get this formula, sorry, okay, okay. Hot mic, okay. All right, so let's say I have this. So what I'm going to do here now is I'm going to just, I want to make L in respect to, T in respect to L. So I have to bring it out from the square root, right? So we have to square both sides first, we just apply our normal mathematics. We square both sides. This is L over G. You know that squaring both sides is going to cancel the square root for this one, but this one still remains squared. Okay, so this becomes T squared equals 4 pi square L. Then we have over G. Okay, we've established that fact. If we rearrange, bringing out 4 pi G, let's ensure that we want to make sure we're getting just T and L at one part. So let's rearrange so we can find the ratios. So this is going to be T squared G equal to 4 pi square L. All right. So we want to ensure that, so if we divide both sides, if I divide here by G, all right, I'm going to be having just T equals this. T squared equals 4 pi square L over G. Likewise, if I divide both sides by L, I try and divide both sides by L, rather, multiply. So I can now find my ratio here and say, okay, T squared over L, I've gotten what I'm looking for, is equal to 4 pi square over G. Don't worry, this is like the simple pendulum bulb is like the last part of this practical physics. Yeah, this is the last part of this part here in simple harmonic motion. You will also just touch the energy of a simple harmonic motion, but this is the last part. And once you grab the understanding of this, it's just the normal mechanics, and we'll be touching the CMS. I say CMS. Oh God, we'll be touching the LMS. We're touching the test questions he gave to us and see how we can maneuver that. Okay, so just bear up, bear up, bear up. So we have this becomes T square, okay, equals 4 pi square over G. So T square over L equals 4 pi square over G. All right, so now, since we're relating the period in respect to the length of the pendulum, look at it here. We're relating the period in respect to length of the pendulum. This guy here becomes a fixed constant for all pendulum for whatever length in a particular part or location. So this becomes a fixed, you know what, let me just write that down. These were relating the period in respect to the length of the pendulum. The right hand side of the equation becomes a fixed, it becomes a fixed constant for all pendulums of whatever length in a particular location. So, okay, this one can go. So we have this. So we have this, right? So that becomes our fixed part. Now, for the second pendulum, we've calculated for the first one, right? So let's relate to the second one. For the second pendulum, which is the one on red, okay? So we're still going to have the same thing. So that will be T2, that will be T2 square. That's the second one now. Over L2, second pendulum, that's going to give us the same thing, the constant, which is 4 pi square over G. 4 pi square over G. So let this be equation, let this be equation 1, equation 2, and while this other one should be equation 1. So this one is for the first pendulum as equation 1. The other one is for the second pendulum as equation 2. So we're good. Now, if we relate them together, we can as well say, okay, T1 relating equation 1, relating 1 and 2, relating 1 and 2. So we can say T1 square over L in respect to the period is equal to, because it's a constant, right? So it's equal to T2 square over L2 because the constants are the same. Constants are the same. So now we can, let's put in, we now have the ratio of time in respect to the length of the pendulum, period in respect to the length of the pendulum. So we can relate to this and we can say, P1, L2. I want to just relate it period to period and length to length. T2, L1. So period to period, I divide here by a period. I want period to relate to period. So I'm going to have just this. So it's going to be period to period because it's just L1 here. And so length to length. So I divide both sides here to by L2 so that it can stay on its own. So this go out. So we have T1 square over T2 square is equal to L1 square. I mean L1 over L2. If we want to make it just period to be on its own, we have T1 over T2. T1 over T2. Now we have to root both sides. So it's going to be equal to the square root of L1 over L2. So this is like a main formula for relating the period between two pendulums with different length. So that is what we practically need to know in simple pendulum. That is it. We just need to know the period and the length. We'll be applying the other formulas that we have from, yes. What about, 1 second. Okay. What about the other previously? Yes. So we'll be applying the other formulas we did in this one. That's a simple harmonic motion. We'll be applying it here. It's just that you need to establish the period. You need to know what period is in respect to length as 4 pi square over G. And then you need to establish this part here. then you can start
Okay.
applying the formulas. We'll apply
Okay.
those formulas.
Please. Those formula that we derive there, like 7 or 8 formula that we derive, we can still use it in the simple pendulum, right?
We're going to use it, yes.
All right.
Mhm. Okay, so this is what we need to know. Let's deal with some questions on the simple pendulum, and let's just kill simple pendulum once and for all. So let's take this. Let's take our first question. Don't worry, you understand it. And yeah, so let's take our first question. So let's say we have, okay, this one says, I think this one should be very easy. What is this? Can you extend, please? This one says, what is the period and frequency of a simple pendulum that makes 40 oscillations in 35 seconds? So this, I think this should be too easy for us. Mm, this is under pendulum. Like you see that it's relatable. They're all relatable. A boy with the other formulas. A boy timed 30 oscillations. You remember what oscillation is? One complete vibration, one complete round, one complete revolution. So 30 oscillations of a certain pendulum price and obtained 1 minute 10 seconds. He also obtained 1 minute 12 seconds. He's having like 3 periods here. And this guy is also obtaining 1 minute 7 seconds, respectively. So after he did the oscillations, you know what I said, how we used to do it in physics lab? We just keep on then checking our time. So the mean period of oscillation or vibration or whatever you call it, of oscillation of the pendulum is, that one is, so it's there. You know how to calculate mean now. Statistics kind of stuff. So the next one is, okay, this one is also the bulb of a simple pendulum takes 0.25 seconds to swing from its equilibrium. That's like its center point. From its equilibrium position to one extreme end. Calculate its period. Okay, that's another one. And then have another one that says a simple pendulum 0.64 meters long has a period of 1.2 seconds. Please calculate the period of a similar, this one now is similar pendulum. See that? And this pendulum has 0.36 meters long in the same location. So you see, it's just like we're going to be applying that formula where we relate two pendulums together. Okay, so that's going to be like a long equation. So let me give it space. Then let's have this one here. A simple pendulum with a period of 2 seconds has its length doubled. its new period is. So we're going to also calculate that one. And let's take this other one. Okay, let's just take like 7. This should be 7 is a perfect number, right? So let me stop here. The simple pendulum has a period of 4.5 seconds, and the length of the pendulum is shortened by 1.2 meters. The period will be, period is 2.5 seconds. Calculate the original length of the pendulum. Okay, so we have how many questions? We have 7 questions. Let's start. Question 1. Okay, let's start with question 1. Question 1, I think this should be quite easy. It says, what is the period and frequency of a simple pendulum that makes 40 oscillations in 35 seconds? So we already know that the formula for period is equal to what? Time taken over the number of oscillations. And what is the time? Here it is 35. And how many oscillations or vibrations? 40. So we have 35 over 40, and that is going to give us what? Can someone help us with that one?
0.875.
Thank you. Thank you, Shaq. 0.875 seconds. Now for the frequency, since we know how frequency relates to the period, so we have 1 over t, and that is going to give us 1 over 0.875. Or if you don't want to calculate it like that, you can just say the number of oscillation over the time, which is 40 over 35, still the same, right? So we're going to have something. And what's this going to give us?
1.14.
1.14. So this is 1.14. Thank you, Shaq. That is 1.14 hours. Or you can say per second. All right. See, that was quite easy, right? So, any questions on that?
I have a question.
All right. Yes.
Okay, I want to understand this period, which is equal to t over right now.
Okay. The
In
time taken over the number of oscillations. Yeah.
yes, in relation to the first concept we talked about, t period equals 2 pi square root of L over G.
Mm-hmm.
And you stated that the other formula is period of a pendulum.
Mm-hmm.
And now this one, t equals t over n. I want to understand the two concepts.
Okay. So remember I said that we're still going to be applying our normal formulas. The main reason or the main formula for period or definition for period is time taken over number of oscillations, right?
Yes, yes.
Okay. So now in this case here, it is not asking us for length, or is not relating the length of the period to another pendulum, which is another second pendulum here. So it's just a plain question that involves frequency and period. It says, what is the period? That's all. And frequency. So we just calculate the normal period. Here now, we're not given the length of any pendulum. So we're not going to use that formula.
Okay, I understand.
Okay. All right. So what about this? This one says a boy timed 30 oscillations. Okay. All right. A boy timed 30 oscillations to a certain pendulum thrice. So that means this boy actually is calculating 3 inputs. All right. So number of oscillations were 30. Is 30, right? So the first one he had, it is asking us for the mean period, meaning that, to calculate mean, You have to add everything you have together and divide it by the total number. So first of all, before we calculate that one, let's check what this well is doing. So he timed 30 oscillations. So n is equals to 30, right? And then the first one, he said 1 minute 10 seconds. So our first period here is equal to, period is t over n, right? So that's going to be 1 minute 10 seconds is 70 seconds. Your time is in seconds, so 70 seconds over 30 oscillations. T2 is going to be, someone can help us with the values. T2 is going to be 1 minute 12 seconds. That's 72 seconds over 30. All right. Someone can also help us with the value. And then T3 is going to be 1 minute 7 seconds. That's 67 seconds over 30. Someone can also help us with this value. So what is T1? Our period, first period.
2.3.
Okay, thank you. 2.33. And what is T2?
2.4.
2.4. That's good. And what is T3?
2.23.
2.23. Thank you, Ishak.
Welcome.
So, to calculate our mean, this is going to be, that is average, right? So we have 2.33 plus 2.4 plus 2.23. And 2.23, right? And divided by 3. That is how to calculate mean, right? So let us add and divide. What we're going to have.
Okay. 2.32.
2 point what?
2.32.
Okay, so we have 2.32
Me too.
seconds. Okay, thank you. 2.32 seconds as our period. Yes, and that is that. Any questions? Okay, good. So it means we're understanding. Let me have a thumbs up if we understand. Thumbs down if we don't understand, please. Okay. All right. Thank you. Okay. Means we're following. We understand. All right. So let's check this one. This one says, um, this one says the bulb of a simple pendulum takes 0.25 seconds to swing from its equilibrium position to one extreme end. And it wants us to calculate its period. Okay, let's see. In order for us to calculate the period here, we need to understand, remember the definition, that the period is the time taken to complete one revolution or one oscillation. Now, if it takes the pendulum bulb, it takes this guy 0.25 seconds, all right, to swing from, let this be point A. So it takes 0.2 swing from its equilibrium position to one end. So comes here to, from point A. Point A is one end. So that means it takes, so this one is going to be 0.25. So that means it takes what? 0.5 seconds. It takes 0.5 seconds to get to the other end. So if it travels here, that's okay, 0.25. It comes here again. That's going to be what? 0.5. It goes here another 0.25, that's 0.75. Then it comes back down to this equilibrium position. Okay, you guys understand what I just did. So the time taken is what? The total time taken to complete one revolution is going to be 1 second. How do I do it? Because this will be like, it will take it 4 times to complete one revolution to get back to its original position. So that is 4 times 0.25. Look at it. Let's say this is, it takes it from O to A first, right? The boy swings it from O to A. Or the bulb is, we swing the bulb from O to A. That is 0.25, right? First one. Then A swings back to O. That's to the equilibrium. And then continues. It goes to B, O to B, right? And then B will swing back to O, to the equilibrium position. That's the start point here. At this side here, the equilibrium position, the start point. So I'm having it 4 times. I will swing from O to A first, and then I'll just let it go. So from here, 0.25 seconds, it comes down here. That's already 0.5 seconds. It goes to B, and then it comes down back to the original position. So it's just like one revolution. So the time it takes to complete one revolution is 1 second, because this is 0.25. This is also 0.25. So that's just 4 now. That's 4 times 0.25. See, I think some of these questions we just require you to kind of break down and reason critically. So this is 4 times 0.25, which is 1 second. So it is 1 second to complete how many revolution? One revolution. Okay. So calculate its period. Time taken to complete one revolution is 1 second. That's 1 second. Bam. Bam. I don't think this question have a lot to it. But I just look at it first and ask your question if you're not clear on what we did.
Okay, I would like to ask, how do you know that the number of times for it to complete one revolution is 4 times? Like, for it to reach to point zero to point A, from point zero to point B, that it has to move a number of 4 times for it to complete one revolution.
Okay, so it's just like you're swinging something. It's not moving 4 times. What it's doing is that it's moving like this. Let me explain it this way. It's moving this way. Let's say I have let this be the B position, and let this be A position. Let this be A position. And then this is how the bulb was in the equilibrium position. So if I kick this thing off, boom, it will go here, right? And then it will come back like this, right? And then like to go here, and then when it wants to stop, it will come back to its equilibrium position here and stop, right?
Yes.
Like when I start and I kick it here, so it will go this way, then swing to B and come back to its normal equilibrium position. So that's just one revolution,
Mm.
right? That's one revolution.
Mm.
Now, if we break down how it has traveled, it traveled from O to A, and then it went back from A to O, which is the equilibrium position. We're going to calculate that time because the time was given to us from O to A. That's one extreme end. Then it went from this O here to B, right? And then to swing back from B back to the equilibrium position O. Do you see it? So it went from
Yes, I
O to
get
A.
now. I get it.
Yeah. So then, yeah. So that's going to be 4 times. That's why we have it as that. Okay. Any questions? Oh, we're good. Okay, if we're good, then let us check this other one. Mm. This question here is telling us, okay, I think I left good space for this. All right. Yes. This question is saying a simple pendulum is 0 point. They call it simple pendulum. Can you imagine? All right. So this question is saying that, okay, my phone is not full. This question is saying a simple pendulum 0.64 meter long has a period of 1.2 seconds. All right. It has a period of 1.2 seconds. And then it says calculate the period of a similar pendulum, which is, so here I'm having the first case scenario and I'm having the second case scenario. So I have the first pendulum. Just remember all the drama we did in this, okay, because we're going to be applying it now in this case. So I have the first scenario to be T1, which is the first instance I have. And says T1 is equal to 1.2 seconds. And then it's asking me to calculate T2, the period of a similar pendulum. Okay, we don't know that one. Now, was I given here? I was given the length for T1. Let me call it the L1, which is 0.64. Write down our parameters. And what was I given here? L2, which is 0.36. Okay. Now, what else? We know that, oh, this is going to involve gravity, right? That equation involves gravity. So we're going to have our gravity involved in this. Okay. So now for the first one, T, our T is equal to what? 4 pi square, right? Our T is equal to 4 pi square L over G. That is the constant. 4 pi square. Okay, it is T square equals to 4 pi square L over G. When we just first bring out that aspect, right? So I'm looking for something we can use to relate, because here now, hot mic. Hot mic. Okay. All right, let me just mute. Okay, so we can continue. All right, so we have equal to G, all right? Over G, that's 4 pi square L over G. Okay, fine. Here now I have 1.2. So that is 1.2 square equal to, we're not given gravity in this equation. We're given the length. We're not given gravity here. So what I'm going to do is I just have to find an equal ground that is a constant that I can use to relate both of them. So this will be 1.2. This one is 4 pi square. Yes.
Okay, why are we not making use of the formula, which is T1 equals T1 all over T2 is equal to L1 all over L2 square? Why are we not making use of that formula? Is there a reason?
There's no reason. We can actually do that. But I just wanted to establish something first. You understand? I'll still come into that where we're going to relate to that formula.
Okay.
Whatever method we use, we're still going to arrive at the same answer. Okay, I'll still come into that. We are going to I want you to establish the fact that gravity can also just remain the same, and there's a way that we can relate to the formula. So I was coming to T1 over T2 equals root L1 over L2. And that's just the easiest. Bam, 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 bam. And we get our answer quickly with our calculators. You know. So, but I just wanted to establish this first. Pico. Calm down, eh? So we have 0.64 here as our L, and then this is over G. For our T2 here, we're going to have just T2 square equals 4 pi square, right, times 0.36 over G. Now we can just see that the G's are the same, right? The G's are here at the constant. Since we don't have any value for the G's, we're just going to make G subject of formula. So this becomes, by the time you cross multiply and you divide both sides, this becomes G equals 4 pi squared because of time, 4 pi squared times 0.64 over 1.2 square. Okay. And this one is relatable to, since we're equating G, we make G the constant. This is 4 pi square times 0.36 over P2 square. So you can then cross multiply and then you find your T2. So you make T2 subject of formula and you cross multiply. So if we cross multiply this, okay, if we use cross multiplication or cross product, and let us make T2 square subject of formula. So this becomes T square as T2 square times 4 pi 4 pi square times 0.64 over equals to, this one is 1.2 square times 4 pi square times 0.36, right? And then this one we can just divide both sides by 4 pi square times 0.64. So someone should help with this calculation and let's see our answer. All we did was we had to we divide both sides, right, by 4 pi square. 4 pi square will just cancel 4 pi square times 0.64. So someone should help with this calculation. Now, we'll notice that all we did was, since G is just there, and we weren't given any value for G, all we had to do was we made G subject formula and we related the first equation to the second equation using G as subject formula. Now, according to what we've proven, when we have two periods, where we have two periods, we have length, we can just relate the formula. Please tell me your value for this. We can just relate the formula to, using our formula T1, like the question she asked, yes, T1 over T2 equals to the square root of L1 over L2. So we can just do this, and then we find this is going to be 1.2. So this is going to be 1.2 seconds. That's 1.2 over T2 equals to root. This is 0.64 over 0.36. So you find that when you find that T2 becomes 1.2 divided by whatever you find, make that subject of formula as well. So someone should give us the value for this, someone should do this, and let's compare our answers. Like, what do we have?
Okay, like on the first part that we did, we cross multiply and we cancel out some values. The answer, I was able to get 0.81.
Okay, so that means 4 pi cancels 4 pi, right?
Yes, sir.
So 1.2 squared times 0.36 divided by 0.64. That what you
Yeah, it's
got?
equal to 0.81.
Okay. So you remember this is t square. Did you find the square root of both sides so that t can stand on its own? So root your answer. You know that we're having square here.
Okay.
You know this was square. So we're going to remove the square by rooting both sides of the equation, right? So this cancels out. So I think you forgot that part. Root your answer. What do you have?
Okay. Okay. Let me 1.2 square. I did 1.2 square.
Mm-hmm.
Square. Then I times it by the value 0.36.
Mm-hmm.
It gives me 1.51. Then I divide it by 0.64. It gives me 0.81.
So you find the roots of answer. Root answer. Yes, the reason is this. You know why? You know we have square here. It's just like you saying, okay, this is what we're left with. You got 0.81, right?
Yeah.
So remember this is t square and t2 square. Remember the square was here.
Okay. Okay. Okay.
So we're removing that square by rooting both sides of the equation. So if we root both sides of the equation, t2 equals root 0.81. That's what we have.
Root 0.81 is 0.9.
All right, 0.9. So 0.9 seconds. Thank you.
Yeah.
All right, so you can as well apply this formula. So who has gotten this one? What is T2? So who has gotten that? Anybody?
It's also 0.9.
Okay, so this one is also 0.9. So now it depends on the one that you like. So we've already established this formula. So if you're seeing two periods and two lengths, just use this one and get your answer. You see, this one is just like one, two, just two steps. Or put it in your calculator and tell your calculator to solve it. It should just give you the answer straight. You can impute a computation like this and it will give you the answer straight. Well, this one here, it's a longer method where you have to relate and deal with and all that. So I was trying to establish the fact that we can solve it normally or we can use the formula that we derived as comparing two periods and two lengths, which is just two steps. So we go for whichever one we understand. We have to be diverse too in our methods. Okay. Do we have any questions? All right. So you see these other two questions here. You're going to do it under 2 minutes. So do these questions and let me know your answer because we're moving to something else now. Moving to something else. Yep.
I can't see the question. No.
Can you see it now?
Yes.
All right. So if we can solve those two, we're going to jump right into um, slope. I think that's another part of practical physics. We jump right into slopes. And I'll be explaining those questions at the LMS, the one we did in our test for practical physics. I'll be explaining all of them. That's question 1 to 20. Oh, first one and second one, right? Yeah. Test 1 and test 2. I know they blocked it, but I still have I still have all those questions. In fact, it's even part of some A-level questions I teach some students. So it's relatable. Remember, the period was doubled. Don't worry, just tell me if you're stuck. You already know the big man in this equation, so the big boss in the equation. So just let me know if you're stuck, and we'll treat it. Let's jump into our practical um, physics, like the questions in LMS. So, are we good? Oh no.
I'm lost.
Okay. All right. So let's deal with it before moving to those questions. All right. So this one says a simple pendulum. Says a simple pendulum with a period of 2 seconds has its length doubled. Its new period is so it has its length doubled. So the first one is we have our T1 equals 2 seconds. We have our L1 to just be L. Did not tell us what that is. We have our T2. I think that's what we're looking for, the new period. And we have our L2 to be doubled of the length. So that's double of the length. That's 2L. Yeah, because the length is doubled, right? So it is asking us to find the second period. So we just relate the formula T1 over T2. T1 over T2 equals to the square root of what? L over 2L. Just know that this is like saying 1 over 2L. So we have 2 over T2 equals to 1L over 2L. That's like 0.5L. So what's the square root of 0.5? This is 0.5L. And then we can cross multiply. By cross multiplication, we have T2 to be equals to oh, this is 2. 1 second. think I've occupied my board already. So this is what this is T2 times 0 root 0.5 L equals to 2 times 1. So we divide both sides by root 0.5. So please help us divide square root of 0.5, 2 divided by square root of 0.5. And what do we have, please? What's our T2? Two divided by
2.82, approximately 2.83.
all right, yes. So we have 2.83 seconds. That's our order period. All right, that's our order period. So let's check this other one. This one says a simple pendulum has a period of 4.5 seconds. When the length of the pendulum is shortened by 1.2 meters, the period is 2.50 seconds. Calculate the original length of the pendulum. Same thing, all right? We just need to find the main length. We said that the length is shortened, all right? So this one here, our first period is 4.5. And we have our length, original length, which is just L. We don't know it. They said the length of the pendulum is shortened by 1.2 meters. When the length of the pendulum is shortened by, so that means our T2 is 2.50 seconds, which was shortened by was shortened by 1.2 meters of the first length. That's exactly what it's saying. That's our L2. So it wants us to find what the original length of the period. It wants us to find L. So we're just going to relate it T1 over T2 is equal to square root of L1 over L2. So it's L we're looking for, so we'll have to square both sides. So we'll square both sides so that the square can cancel the square root. We're going to have T1 square over T2 square equals L1 over, this is L minus 1.2, right? So we just put in our T1 is what? Our T1 is 4.5, so we have 4.5 square. 4.5 square over, our T2 is 2.5, so we have 2.50 square equals L1 over L1 minus 1.2. So we just cross multiply here, and we have, this is going to give us L1 minus 1.2 parenthesis 4.5 square equals L1 times 2.50 square. So let's open that. What is 4.5 square, please?
Twenty point two five.
20.25.
All right, so L1 times that, we open the parenthesis, that's 20.25, then minus 20.25 times 1.2, that's 24.3, right?
24.3.
Okay, so we have this one to be 20.25 L1, then this one is just 2.50 square. Give us what?
6.25.
Okay, so we have 6.25 L1. So all the L1s, we take it to one side, and then the other one, when we bring it to the other side. So I'm going to have collect like terms. Collect like terms. So this is going to be 20.25 L minus 6.25 and 6.25 L. So equals, take this one to the other side, that's 24.3. And so this is going to be what I think this is 14, right? When you subtract 14L equals 24.3. So our original length, we divide both sides by 14. And what do we have? So L1 equals, original length equals 24.3 divided by answer. That is giving me 1.735, approximately 1.74 meters. So this is 1.74 meters. Hey,
The 1.74.
yep, 1.74 meters. That's going to be our original length. So whenever you're just asking for this, you already know what to do. So let's dive into some questions in that LMS. Okay, so one second. All right, so our first question in the LMS is saying that we have a non-linear, you know what? Let me, okay, one second. Let me see how I can share this. Oh, this is 11:15. If you need water break, 10 minutes, you can go for water break. Oh. Just come back in 10 minutes. Let's clear. Let me explain the questions in the elements and we'll be out. There are like 40 questions in those tests. So there are some that talks about um, coordinate equation of lines. So it's something I can just explain. And then you'll be seeing some questions in simple pendulum. More questions in simple pendulum there. So yeah. So if you want to take a break, you can come back. If you want to take 10 minutes break, get water or get coffee or something, you can come back in 10 minutes. That is 11:25. All right, so 11:25. Meet you guys here. Okay. So
Aku belum sini, ini sebenarnya aku goodbye. Isnan apa nanti macam ni kita kong ni emo. Sir gini ya macam oh, nang wala. This chen
Uh,
ni kami cak oh.
that is strong business Igbo we have here. Okay, we have 5 minutes. All right. So let us get to it. So let's get to it. Let's get to it. Uh, Let me see. Okay. So we have. Oh, sorry. This is not for us. This was our physics class we had for those that came for the class. I have some questions in there. Some questions in practical physics LMS. No, 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 not all this. No, no. Uh-huh. Now, this is where we start. Physics 107. So, I'm going to just explain some questions and some concepts here, some topics here, so we can understand this part. So, read this question. This question says, a nonlinear relation y equals ax squared plus bx. We are seeing a quadratic. If you're in the maths class, you understand that this is a quadratic, right? Now, okay, it now says it's best linearized for slope determination by plotting. Okay, so I'm going to explain it here. Now, when we're dealing with the slope, okay, when dealing with slope, so when we're dealing with the slope, this, if we have a graph, um, when you have ax squared, y equals ax squared plus bx plus c, or you're having a quadratic, all right? So you're trying to make this be in form of a straight line, all right? So if you're looking at, according to the question, it says this is a quadratic equation. According to the question, it says y equals ax squared plus bx. Whatever you're plotting against the horizontal axis, this is our graph. Let's put this as our graph. Whatever you're plotting against the horizontal axis has to be in respect to that horizontal axis. And if we're relating this to the equation of a line, the equation of a line is what? Y equals mx, which is the gradient or the slope. According to mathematics, call it m, physics call it slope. Mathematics is gradient, physics is slope. So mx plus c. This is the equation of a straight line. This is how we determine our slope. So the slope is always the coefficient of x. So what we're going to do here is we're going to divide this equation by x. Okay, but divide the equation by x because we want to find the coefficient of x. So according to the question here, whatever you're plotting, it says a non-linear relation. Take note of it just in case it pops up. A non-linear relation y equals ax squared plus bx plus c. Okay, it means that we're going to, this is our x-axis. So what we're going to be plotting will be y over x in respect to what? Our x-axis. So it's going to be y over x versus, it's going to be y over x versus the x-axis, because this is our x-axis, right? So it should be y over x versus the x-axis. So, and that is a, because you're plotting in respect to the x-axis. That is just equation of line concept. Okay. In question 2, we'll talk about the slope. You'll see it there. Question 2 says if a straight line graph has equation y equals mx plus c, and both x and y have uncertainty. All right, so if we have a straight line graph, which is y equals mx plus c, and both x and y have uncertainties, it says the slope uncertainty is best obtained using what? So for things like this, oh, this is what I'm meant to be sharing. Our question 2, right? Sorry about that. So, 1 second. So the slope uncertainty is best obtained by now. The thing is, when both variables have uncertainties, when the variables and the slope have uncertainties, for those that don't know what slope is, let's say we have two lines here. Let's say we have two locations or 2 points here. To calculate the slope here, we need to just find, it's just like you calculating, this is our slope. You're calculating the distance in y in respect to the distance in x, or the change in y in respect to the change in x, which is the change in y is y2 minus y1 over x2 minus x1. That's the change in x. So that's actually how to calculate slope, just in case you're asked. Okay, so this is actually how to calculate slope. Please remind me to be flipping, changing my board, because sometimes I'll still be in the presentation while I'm explaining the thing on the board. So now, in order for you to, when we have both variables and when both variables have uncertainties, the standard graphical method involves drawing the best line. Okay, so we draw the best line, then we draw with steepest and shallow possible slope. What this means is that in some graph, this is what you're going to have after you finish plotting. Let's say you have this. Let's say you have this. You'll not be seeing some plots here, and you'll be seeing, okay, let's say you have this. You'll see some plots here, and you see some plots here. So the question is saying that, okay, when we have uncertainties like that, how do we use it? The best thing is to use the maximum and minimum slope method, which means that you only plot the first three that is correct. If you see a first three that is correct, just plot it out. Then we can have we call it a minimum and maximum slope method. So the other ones that are outside, just patch it. As long as you can see three or four that matches, plot your graph. That's it. So in situations like this, what we use is the maximum and minimum slope method. So just take note of the question, take note of the concept, just in case. Okay, this is the question, just in case. And to the next. Now this one says the gradient of a graph plotted from y equals k over x after linearization. What does it represent? All right. So after linearization, so linearize means you have to make the constant. So linearize means to make the constant subject of formula. So if this is we're going to look for the constant. What is the constant connecting y and x? And that is k. So that's constant k. Okay. So we're plotting y against 1 over x. That's the meaning. And that is just k. There's no much thing to this. Just like you find the ingredient. So there's no much thing to it. Okay, 1 second. So this other one says when, okay, I think you guys should be good with this. Someone should give us the answer.
Obviously, I was not clear with the previous one before now.
Okay, sorry. Did so it says when linearizing, all right? The intercept ideally equals what? What is the ideal to this intercept when linearizing? Okay, let me just help you out. When you're going to linearize this, remember how we said we had to linearize this other one by finding the constant k. In this situation here, where we have 4 pi square over gl all at once at the same time, we don't fully per se have a constant. Okay, see, just right here. we don't fully per se have a constant. So whenever you're linearizing, all right, because your equation of line is always y equals mx. So there is no constant term that is added to this. Okay, so the line is, 1 second. Mm, oh, yes. So tell us about it. I'm not going to tell you the answer to this. Help us out with it, please. I think they've locked all these questions in the LMS already. And I noticed they were locking questions. I just had to go and get this one sharp.
I think it's 0.
Zero, yes, it is zero because um, there is no constant term that is added to this equation. So it is actually zero. Yep, that is correct. Now, look at this question. The question 5, it says, okay, look at the question. Question 5, it says, the best fit line that question, yes. Oh, not not per se the slope. It's because of the constant. So we're not saying the slope is zero. We're saying that it is going to pass through the origin. So this is if we have the slope or we're plotting, whatever we plot is going to pass through this origin. Okay, so it's going to pass through the origin. That's what we're saying. To linearize. Okay. All right. So let's see. So for this one says a best fit line that does not pass through the origin, despite theory predicting so, suggests that what? So it does not pass through the origin. And theory is saying that it's supposed to pass through the origin. So what's that? I mean, is that a random error? He talked about it. Is it a random error? Is it a systematic experimental error? Is it improper scaling or numerical rounding? It's not random. It's not improper scaling. They call it a systematic experimental error. All right. So when you consistently shift from the origin, this is it. So when you're just moving away from the origin, you're just consistently shifting from the origin. All right. And this in theory or in the formula given, our theory is predicting that, oh, this thing is meant to be zero, meaning it's meant to pass through the origin. So that means there has been a bias in the measurements. So that is known as a systematic error. All right. So that is known as a systematic error. Your theory has actually predicted this thing is meant to pass through the origin. This slope or this line is meant to pass through the origin. But what you're getting is a shift from the origin, a non-zero intercept. So that means something is wrong. So all those kind of errors is called the systematic error, which is systematic experimental error. I think he made mention of that as well. So check this. Question 6, in determining the slope, in determining slope error, points chosen should be what? So the best, look at this slope here. Look at what I'm going to do. If I'm the one going to calculate my slope, I'll just look for the end points and the beginning points. Bam. And I'll use it to calculate my change in y over my change in x because I don't need stress in my life. So in order for you to calculate slope, it's going to be what the farthest and the farthest apart along the line. So the place that you know that, oh, these are the two endpoints, the farthest apart, just use it and calculate your slope. So you'll be getting your distinct answer and not stress yourself or stress your, yeah, stress yourself. So now there's something we also known as fractional error by absolute value of exponent. This is the equation here. Yeah. Okay. That's the equation there. It says if Q equals a square b to the power of -1/2, that is like root b. It says the fractional error in Q is, so in order for you to calculate fractional errors for powers is like this. These are powers. to the power of 2 to the power of -1/2. Those are powers. All right. Now, in order for you to um in order for you to understand fractional errors, what you need to do is if we have an error, for instance, this is qa to the power of 2, q equals a square b -1/2. That's what the question is giving us. And it wants us to find the fractional error. So to find fractional error, to find fractional error. Okay. So what you're going to do is you're going to get the absolute value of the powers. That's the exponent. You get the absolute value of the powers. All right. And then you multiply it by the fractional error itself. So what I'm going to do is I'll say the value of the powers, which is 2. All right. Then I multiply it by the coefficient. What is carrying that 2? That's the value of the exponent. What is carrying the 2? I multiply it by that. So I multiply it by a, or we call this the change in a over a. Then the same thing with this one. The value here is what? -1/2. Absolute value is -1/2. And then I multiply it by what? By the change in b over b. So this is how to calculate fractional error. You take the powers and multiply it by the change in the whatever is carrying it. That's it. So the correct option for this one is going to be okay. So this is going to be a. That is 2 change in a over plus 1/2. It's actually meant to be -1/2. There's a mistake here because this is -1/2. So this is meant to be -1/2 times change in b over b. But that's the closest answer. That's what I'll pick A. So question 8, the dominant error of vernier caliper measurement of internal diameter is. So dominant error mostly is, some people will say is the 0 error and all that. But for internal diameter measurement, okay, most common dominant issue is mainly the 0 error, right? Because the jaws do not align perfectly at 0 when they are closed. So it is this. But when you're taking in the measurements, all right, we can also make a mistake of the parallax error. So for this one here, we're going to be using the parallax error because not 0 error. 0 error has to do with the jaws, all right, while parallax error has to do with the measurement itself, the diameters, the numbers, and the measurements itself. So let's not make mistake of picking the 0 error. Answer is parallax error if you see a question like this. But mainly, a lot of people will pick 0 error because, yes, I mean, that's actually was the dominant error affecting. I think the question was not set properly, but that's the dominant error affecting vernier caliper measurements. It's mainly the adjustment of those jaws in the vernier calipers. So that's meant to be 0 error. We also did that in school then. Then we have now, okay, so it says here now, if the vernier 0 lies 0.03 centimeter to the left of the main scale 0, the 0 error is, you see this? You see this? So I think our professor made a mistake in this question because the answer here is meant to be 0 error. So I think he made a mistake. They should change this the way he set the question. Well, they will not even change it. Why am I complaining? I'm not the professor. So now question 9. It says if the vernier 0 lies 0.03 centimeter to the left of the main scale. All right. It says the 0 error is, so whatever lies on the left is always a negative. Whatever lies on the right is always a positive, okay, of the main scale. So if it lies on the left, just know that's a negative. If it lies on the right, just know that's a positive. So our answer here is going to be, since it lies on the left of the main scale of 0, it's just like you having your graph now. Just like dealing with your graph. Whatever is on the left side of the x-axis is our negative x. So once it passes this origin or this 0, negative, right? So yeah, So that's going to be negative 0.03. So question 10 says the corrected reading from a vernier caliper with, why did they pack vernier caliper in this? A lot of vernier calipers. The corrected reading from a vernier caliper with negative 0 error is obtained by, so how you do this is, if you want to obtain, there's a formula for it though. We always solve this in class. So what you do here, vernier caliper or vernier caliper, okay. So now for this vernier caliper here, what you're going to do is you're going to subtract, 1 second. So you're going to subtract, it's going to be like this. Whatever you read or whatever you look at, how would I put it? Noted reading, that's how we put it. Noted reading, that means whatever you read minus the 0 error. So whatever error is on the 0 scale. Okay, so noted reading minus the 0 error. So since the error is negative, all right, so it depends on where it is. So the corrected, look at this one, it says the corrected reading from a vernier caliper with negative 0 error is obtained by, so is it adding the 0 error magnitude? Is it subtracting the 0 error magnitude? Ignoring the 0 error, rounding up the value? How is it obtained?
B.
B. Okay, so if you say it is obtained by subtracting the 0 error magnitude, so this is how it's going to be. Let's say we have our noted reading to be R, right? And then we have this to be, okay, so we have our 0 error. If it's negative, so let's say it is negative 0.03, like our previous question.
You're still on the presentation.
Oh, thank you. So let's say we have, thanks. Let's say we have our noted reading to be R, and then we have this, we're subtracting the 0 error. So this turns out to be plus 0.03. So at the final level of that equation, did we add or did we subtract the 0 error?
It's addition.
Exactly. That's the confusing part. So we know that, yes, it is observed reading minus 0 error, but our final thing is going to give us a plus, right? So since the 0 error is negative already, all right, all we need to do is we just add it. The formula says you subtract. So by the time you subtract, the reading you're going to get, all right, is obtained by just adding the stuff. So you just add the 0 error to it, to whatever you get, and you see your reading. So adding the 0 error magnitude. But most people go for subtracting the 0 error magnitude, and that's like an X. Yeah, that's like an X. So let's move over. So this one says, hey, how many questions do I have here? Okay, I still have more questions. Okay, so this one says, which transformation converts y equals a Euler negative bx into a straight line form? Now, remember how we talked about straight line equations, where we said equation of a straight line equals mx plus c, right? So I would say that. So making y subject formula it's good. So the first thing you want to do is, now we have that we have the a to this exponent negative bx. For things like this, it's just a natural logarithm that we find, right? Because of the Euler that we're having here, we're going to just be finding the natural logarithm in both sides. So normally our straight line is what we're plotting y against x, right? So it's mainly y versus x. So it's y against x that we're plotting. But we're going to be taking the log because of this. We're going to be taking the logarithm of both sides. So this is going to be the natural logarithm that's in y, which is equal to same thing in natural logarithm in y equals to um in a Euler negative bx. So as long as it matches the linear form, this is the thing about natural logarithm. When you calculate in y and you have an equation like this one becomes in a. All right. Now the Euler is this Euler here is representing natural logarithm. So when you introduce the in, it's no longer there. Okay. And the powers just come out as what? As bx. That's how it is. Negative bx rather. So Euler here is already the natural logarithm, so it cancels out. So this becomes like in y equals in a minus bx. So that power just comes out. That's under transformation and logarithms, logarithmic equations. So it just comes out like this. And if you look at it carefully, this is very close to our mx plus c formula, like equation of a straight line. So our answer here is going to be, we're going to be plotting what? In y versus x. That's what we're going to be plotting. In y versus x. So if you selected that in your test, wow, very good. It means you detected those questions very well. Okay, let's see this. It said a graph plotted with unequal scale divisions primarily affects. So just look at this. Remember this. I think they've asked this question before. Remember this. It says, look at this. Remember we have plots here, plots here, plots here. We just need to find 3 or 4 that can match and plot our graph. So that means it's going to affect the accuracy of the slope. So we cannot really determine the right slope when we are having different plots, right? So it will affect the accuracy of the slope or determining the right slope. Okay, so that one is just a normal question. Question 13 says, the uncertainty in the intercept of a straight line graph is minimized when, so it's minimized, it's the same question with this. Accuracy of the slope determination. So if the uncertainty will be minimized when the slope uncertainty is minimized. When we say uncertainty, meaning that we're having different plots, we're not sure, it's not clear, it's uncertain. Okay, so the uncertainty in the intercept of a straight line graph is minimized when the slope uncertainty is minimized. When it comes to the graph and straight line graph, just be relating slope and the stuff together. So So sorry about that. I just had a little glitch. I don't know where that came from. I had to switch my networks back. So this is where we were. Okay. So, as I was saying, so when we have that, we all remember, I was trying to say, we all remember this when we did percentage error in school, where we had our percentage error, that's percentage error will be equals to error over actual value, error over actual value times 100%. And that is equal to the error is the change in whatever we have over the main actual value times 100%. So that's how we calculate percentage. So that's actually how we calculate percentage error. Just normal math for this one. So that's change in m over m times 100%, right? Like that one is too common for us. Okay. Now, let's see this. It says in the experimental linearization, logarithmic plotting is preferred because logarithmic plotting is preferred because the reason why they prefer logarithmic plotting is because it normally put in power laws into linear form. Look at the way we just changed this one. Look at the way we changed this power law here. This was in powers, and we just changed it into a linear form. We converted the entire thing to a linear form from powers, which was y equals a Euler negative bx. We just converted the entire power whole thing into a normal linear equation. Look at it here, the normal linear equation. So that's one of the reasons why experimental linearization is preferred. It converts power laws, okay, power laws into linear form, okay, just normal linear form. So for instance, if you're having something like this, where are you? Okay, so for instance, if you're having something like this, let's say you're having y equals a x, let's say to the power of n, and we just put in our logarithm. So this can just give us log y, okay, equals log a. So just bring it out in a linear form plus, right, n log s, n log x, and that's it. Okay. No much distance to bring it in a normal, form. Okay, then so let's check this other question. So that's converts powers into linear form. Random errors in graph plotting are identified by random errors in graph plotting. Scatter of points about best fit line. That's just your answer. We've talked about this like 3 or 4 times now. Dot dot, like different plots everywhere and all that. So question 17. The least count of a vernier caliper increases. Mona go no vernier caliper. The least count of a vernier caliper increases when we have, the least count will always increase when there is more divisions. So if there are more divisions, not when the jaws are tightened or when there is zero error. So when there are more divisions, we're going to have a least count in our vernier caliper and all that. So that one, like, let's say least count is calculated like, let's say we have the value of scale division divided by the number of divisions. So the least count of a vernier caliper increases with what's that? Yeah, with more divisions. Thank you, Treasure. So when there are number of divisions, the least count of a vernier caliper increases when there are more divisions in the equation. But in here we have the number of vernier divisions decreases. Yeah, this is a twisted question. Professor dropped here. So it's meant to be the number of vernier calipers. Okay, look at this. I know the formula though to calculate vernier caliper least count. When you're trying to calculate least count, we have least count for vernier calipers is the value of what we have divided by the number of divisions. All right, divided by the number of divisions. So let's say we have a 1 scale here. So if the number of the denominator, all right, if the denominator decreases, okay, so let's say the number of division decreases. So let's say this is number of divisions. We're having let's say we had 2/3. All right, we're having 0.01 over 2 rather. Let me start with that one first. That is something relatable with vernier caliper, not 2/3. All right, so let's say we're having 0.01 over 3 and all. So the number of divisions, if the number of divisions is less, let's say this is the only number of divisions that we have here. So if the number of divisions is less, okay, and if we're comparing this to, let's compare this to, let's say we have 1 over, we're now having 0.01 over 2, 0.01 over 3, 0.01 over 4. So the least count, we can calculate the least count like this. So we add all these divisions together, add your divisions here together, and add the divisions here together. And let's see which one will give us the least count. We can calculate it using that formula. So the value divided by the number of least count. So I have 0.01 divided by 2 here plus 0.01 divided by 3 here. And then I have 1 divided by answer. So here he's giving me like 120, right? Okay, so let's check this other one. So I have 1 divided by 0.01, 0.01, sorry, 0.01 divided by 2 plus 0.01 divided by 3 plus 0.01 divided by 4. Okay, so I'm having this, then 1 divided by answer. Okay, so I have this to be 92. So this is our least count. So exactly. So that becomes our least count. So here now it's meant to be as the number of divisions increases, what he put here as decreases, and that should be the least. That should be the least. That is going to be the least number that is attached. So yeah. So that's going to be like our closest answer, but it's meant to be when the divisions actually increases because we have proof here. So 92 is the least count. We have more divisions and 92 is the least count. And then this is 120. Oh, no. So that's the formula for least count though. Okay. Closest answer is D, but it's incorrect. They should also check it. But who am I? So now question 18. Abi, who are we? Question 18, it says a straight line with large slope uncertainty. The same thing now, we already know the answer to this. But you don't even need to look at this question. That's for experimental precision. Question 19, please. Now, it says, which condition invalidates slope-based constant determination? I think the answer to is very, very, the answer is observable. Something we can note is obvious. That's called the experimental plot with assumption. Okay. I don't think there are much things here. The principal advantage of graphical error estimation over analytical method is that advantage. So graphical error estimation. That's what we did, like using the 3 points, just plot the 3 points. Over analytical methods is that it accounts for experimental scatter visually. You know, that removes systematic errors. No, it doesn't. Eliminates calculations. No. Improves list count. So that should be D. Accounts for experimental scatter visually. Or what do we think about that one? It's an open question for us, because okay, so yeah, okay, yes, somebody. D, right? Same thing. I was thinking accounts for experimental scatter visually. That was same thing I was thinking. All right, so let's see this. Yeah, so it's already 12:05 at this point here, because I still have some other engagements and all that. So it's already 12:05. Although what I'm going to do is the remaining questions, because I still have some questions, I think from the second, that talks about the ballistic pendulum, velocity after impact. Uh, yeah, yeah, yeah. Okay. You know what? We can do that. That's from the second LMS. We can do that if we still have time. So if you need 5 minutes or 10 minutes, we can just do that. So we can just touch all those ones if we still have time. So for those of us, yes, that we need breaks, you can go on break now. Just 10 minutes, another 10 minutes. So we'll come back and finish the remaining LMS question there. So let's just analyze it. Just 20 questions remaining in test two. We analyze all those ones, and then we'll just kiss ourselves goodbye and wish ourselves luck for physics. And maths will be for that math. We've already done the class in math. So I have first class that I shared that was free. Then the other class was the paid class. So I have to collect permission from those I paid if I can share it, which I think some of them are in this call safe. So and then I'll share it on the group. So yes, let us take 10 minutes. Let's take 10, please. Right. Right, welcome back. So, welcome back. Let's do with those remaining questions, and we did it. It's gonna be a go. So, first question says the collision phase of a ballistic pendulum experiment is analyzed using which fundamental principle? So you see this pendulum that we've been treating since. Well, so you see this pendulum that we've been treating all through. So the question here is saying that is it conservation of mechanical energy, conservation of um, linear momentum, angular momentum, conservation of power. Now, here is relatable to a conservation of momentum. Why do we say momentum? Because there's going to be a collision for bulb, like an external force. Remember Newton's law? Will hit the pendulum bulb, it starts to come back and forth. All right, so that is that linear is a linear momentum question that we have there. So anything momentum, remember when we're dealing with it in physics, we treated that part under Newton's, talked about that part under Newton's, and when fighting that aspect in physics. So now, this other question here telling us that, okay, question 2 now says, bullet of mass. Hello? Hello? Yeah. I'm in a class. Class, I can't chat. I'm in a class. Like, I'm in a class. What's up? For phone. Wait, hold on. I can't really help with that. All these students, why do you carry phone to school? All right, so I should help you build your phone now. Oh, wow. So it says if a bullet of mass m embeds into a block of mass m, the immediate velocity after the impact is given by which of these formulas? So let us try to understand that part here. So now, there's a part here we explained about this momentum thing. Just trying to see our entire board. Okay. I don't know where it went to, but I know that we've treated something like that before. Oh, this is maths. Well, when we're dealing with physics and all that, we also treated that aspect. But since it is lost now, this board is actually infinity. So since it is lost, well, I'll just explain it here again. All right, so it says immediate velocity after impact. All right, so now the thing is, by conservation of momentum, we have a velocity, we have a momentum before collision, and we have momentum after collision. All right, so we have momentum before collision and momentum after collision. Now, this one is saying here, the question here is saying if the bullet of mass m embeds into a block of mass m, what is the immediate velocity after the impact is given. So if this is the block and then this is the bullet comes and embeds here. So there has been a momentum which is mass times velocity, then plus the mass and velocity of this block was 0. Then after momentum, they're asking us for the velocity. So we're going to have the mass of the bullet plus the block plus the mass of the bullet, and then we're asking for the velocity because now the block moves. So there is what we call before collision. I'm sure those that have been in the class, you would understand this. Before collision and then after collision. So we have before collision and after collision. So now that the bullet is embedded, it says that which of the formulas are going to be is going to be used. Now for this kind of equation, we have the mass. This is it here. So we're looking for v. V becomes, we divide both sides by m plus m. So this is m plus m. So our velocity is going to be mv over m plus, just as if we're calculating our normal linear momentum using Newton's second law or first law, and that is a. That is a. So now we have another question here that talks about 1 second. We have another question here that talks about, it says the kinetic energy is not conserved. Okay, question 3. Kinetic energy is not conserved during the impact in a ballistic pendulum due to what? This question also have an error. So kinetic energy is not conserved. The kinetic energy that is not conserved during the impact in a ballistic pendulum is due to what? Now it is due to what? Is it internal deformation and heat loss? Is it air resistance? Is it conversion to gravitational potential energy? Is it conservation of impulse? Okay, so the reason the reason kinetic energy is not conserved during the impact in a ballistic pendulum is because of there is going to be heat loss. Sorry, there's going to be heat loss, and there's going to be um, deformation. All right, so there's going to be heat loss and there's going to be deformation. So in an elastic collision, and, and this boy here, sorry guys, 1 second. May God bless me with all these students. Okay, so the reason the kinetic energy is not conserved during the impact in a ballistic is because of there's going to be deformation and there's going to be heat loss. So look at this now. Let me explain. When in the pendulum bob, when there is an impact to the pendulum bob, especially when we have an inelastic collision, kinetic energy is not conserved because some of it is converted into non-mechanical forms of energy, such as heat, sound. So when we hit this bulb, we have heat loss coming out of it. We have energy also felt from it. So, especially when this is elastic, there is a deformation coming out from it. So it depends kind of so formation and heat loss is all right. So if we have our next question here talks about, I don't know. Our next question here talks about question 4. It says the maximum vertical rise of a ballistic pendulum after collision. The maximum vertical rise of a ballistic pendulum after collision is obtained by applying which of these? Is it the Hooke's law? Is it the conservation of mechanical energy? Like I said, when you have in an inelastic collision, that's the ballistic pendulum. When you hit it, like the previous explanation I made, the kinetic energy is not conserved. Some of it is not conserved because some of it is converted into mechanical forms of energy, such as heat, sound. Right? It is, there's the deformation of the materials, so that is converted into mechanical forms. So here now, when they're saying the maximum vertical rise of a ballistic pendulum after collision is obtained by applying, just know that it's obtained by applying what the conservation of mechanical energy. Bam. Because after the collision, all right, the kinetic energy is converted into normal potential energy. So this is it here. Let me explain this. So at this point here, when we swing or when we hit this ball, when it gets to this point, it's already at its potential energy. It's converted because like this is at rest. When it begins to move again, it changes back and converts to kinetic energy. All right, to this part here, it goes back to what? Potential energy. When it comes back again, it changes back to what? Kinetic energy, and then it returns to the original position as what? Potential energy. That's energy at rest. You see, there's a conservation of mechanical energy there. So um, um, not all kinetic energy. So this other question says, yeah. Okay, so this is a formula that we need to know. This is a formula. Question 5 says the expression, sorry. Question 5 says the expression V equals M plus M over M root 2GH assumes the ideal condition. So what is the ideal condition for that expression? So if you just see M plus M over M, you know that, okay, this is talking about an energy loss after collision. Remember when I talked about the conservation of energy, where we have momentum before collision and momentum after collision. So if you, this formula here with 2GH, to start proving the formula is going to be a long way. So this is actually what's, this is a loss after collision. So we use this to calculate the velocity of a loss after collision. M plus M over M, that's mass of the block over mass of the moving bullet or moving vehicle or moving motion body, okay, over M, then root 2GH, that's the height of the pendulum. So most of these things are also coming out from pendulum. It's just that it's theoretical part of pendulum. So this is about negligible. Okay, here they wrote it as negligible energy loss after collision. Just loss after collision. We do term it as in normal physics. Okay, so for okay, that was question 5. So for question 6, we have the dominant source of systematic error. I think we should know this one. Says the dominant source of systematic error in ballistic pendulum experiment arises from. So I think we can answer this. I think this one is easy for us to answer.
I think it's parallax.
Parallax, yes. Correct. It is parallax. Parallax is that main error. That's little error that we can make with our eyes, especially during experiments and all that. So yeah. So yes, that is parallax. So this other question is saying that question 7 is saying the simple pendulum behaves as a simple harmonic oscillator only when we have this, only when we have what? An angle. So the reason why a simple pendulum is going to behave as a simple harmonic motion is when we have an angle. All right, when the we have the restoring force is like almost the same thing as the displacement. So For instance, let's use our formulas that we've done in simple pendulum, understanding of simple pendulum or simple harmonic motion. Yeah. So now, when theta here, okay, it is true when, look at this now. Let's say we have this and we want to connect this guy. Okay. So this angle 90. Okay. This is our angle 90 degrees. It should be our angle. Now, when we want to calculate something like this, we're going to use, because it's a vertical thing. So when the restoring force, the centripetal force, when the restoring force is almost the same thing as a displacement, when our theta, all right, now this for concerning R is going to be like, when remember our SOHCAHTOA, this is our vertical axis in physics is always sine. So anything vertical, we're relating this part now. So theta here is going to be with sine theta because it's related to the vertical aspect. You know, I told you two things. There's a vertical aspect in physics and horizontal for those in physics class. And we have sine theta and that is cos theta. So sine theta is always for our vertical aspect. When we're dealing with this kind of angles, it's always sine theta. So imagine our sine theta is now the same thing as theta. So what it means is that the sine theta is closing to this aspect here, to this theta here, the angular velocity that we have here. So imagine sine theta is approximately this. The angle from here to this distance is getting to this. It means that the distance is no longer at this point here. It's now getting close to equate the displacement at the side. Since the theta you found here, or the angle you found here, is approximately to the middle angle that is originally having. So the only way a simple pendulum will become a true simple harmonic motion is when the force is proportional to the displacement. So when we have sine theta approximately equal to theta, like measured in radians, it's as if the distance are now getting equal. So that is when we now say, oh, simple pendulum will behave as a simple harmonic oscillator or simple harmonic motion when our sine theta is approximately theta. When sine theta is approximately theta. Now, the approximation of sine theta to approximately theta is typically considered valid for all angles less than about 15 degrees or 0.226 radians. So it's whenever we're trying to approximate that, usually the theta is usually small. The angle is small when we're approximating sine theta to be equal to theta. So it's usually very, very small. This now brings us to our next question here, because the next question actually relates with this. The next question says that approximation sine theta to theta is valid when the angular displacement is, remember, it's usually less than 15 degrees. That will make it approximately, okay, and theta will be approximately to theta. That's just a standard. So it is when it's actually very small, when the angular displacement is very small. Okay, at about 15 degrees or 0.26 radians or something like that. So when it is actually very, very small. So just in case we see that. Okay, then let's take the next question here. Says, all right, I think you're going to answer this one. This one says the linearization of simple pendulum data is achieved by plotting what against what. So that is for you. We've done a lot of T squares and L's and all that. So I think that's for you. So what do you think the answer is? What are we plotting?
T against L.
Is it T against L or
I think it's
when
just
we
square
start?
against L.
Yeah. T square against L, because remember this. Where do we start that formula? Okay, so the L was inside square root originally. So to bring out the L, it had to be what? T square against L. We had to relate it to square to L. You see this? When we were finding the ratio of T square to L. So when you're plotting it on your graph, you're plotting the period, the square of the period against L. Okay. One second. One second. All right. Hey, people are serious. So some people brought MTH 101 Elementary Mathematics Complete Assessment Compilation. This is serious. Okay. And if are really panicking for this mathematics, so it's not so loud like that as it seems. All right, so let's check this next question. It says the slope of a t square versus L graph is equal to what? You already know this. You already know this. Please, this is, I think this will be 4 square over G, not 4 pi 2.
4 pi
Okay.
square over G.
Oh, yeah, that's the answer. And that was an error from their end. So that would actually confuse someone now. So 4 pi square over G. So What else? Okay, we had 10 more questions under this. 1 second. All right, so check this one out. So this one says the experimentally determined value of G is most sensitive to errors in measuring
Length of the pendulum.
length of the pendulum. So why do we say length of the pendulum? Why not the time period? Is there? I think that is debatable. But in experimentally determined value of G, the most sensitive errors in measuring, is it the length of the pendulum or is it the time period? The time it takes that stuff to complete one resolution. Because in our formula we have G to be 4 pi square L over pi square. So over T square, right? Rather. So the time period is actually squared when compared to our gravity. We actually solved that when we're dealing with this first equation here. This other equation question that was very long, where we had to relate the gravity. Okay, where we had to relate gravity to the two equations, finding T square. Okay, so then are we going to say the length, or we're going to say the period that's going to determine our gravity? What do you think? The time period or the length of the pendulum? Actually, it's the time period. Since no one is actually answering, I think we're all tired. Don't worry, don't worry. We'll soon finish. We just have a few questions to go. I want us to just cover all these ones. Then we're already done, though. We just want to cover all these ones. So it says here that the restoring force in a simple pendulum is directly proportional to displacement. Right? Restoring force in a simple pendulum is what? Directly proportional to the replacement. Only when we've talked about it before. Remember when I said something will be very, very depending on the theta? So it's still the same, it's still going to affect. So only when the oscillation amplitude is small. Remember when we talked about the sine theta? Where is it? Approximating theta. And I said it's only when it is very, very small that this can actually happen and this can be correct. So if that happens, it means the amplitude too has to be very, very, the oscillation amplitude has to be very, very small. So it affects every part. So now we go over to the next question. We're going to hurry. And the next question here is telling us about Hooke's law. It says Hooke's law remains valid only up to the what part?
They are still on the solving body.
Oh, sorry. Say Hooke's law remains valid. Okay, Hooke's law remains valid only when up to which part? So Hooke's law actually has to do with the stress and strain. It has to do with the force and elasticity of an object. When the object reaches its limit, we call it the limit of proportionality. When it reaches its limit of proportionality, all right, it ends. The elasticity ends at the limit of proportionality. That is the next thing is entering its breaking point. Boom. So it is only valid up to what? The limit of proportionality. That's when you extend the rubber band, you extend it to an extent where it now becomes plastic. So now, if you continue extending any little force or any more force after it has gotten to its limit of proportionality, that's like it's getting to that point, limit, that reach the limit, it will change into plastic and boom, it will break. Becomes, it gets into the breaking point. Okay. So that is so if we extend the rubber band, extend it, it will get to a part, it will reach the limit of proportionality. Limit of proportionality is also known as the elastic limit, like it will get to that limit. So imagine when you extend the rubber band, what happens? You've deformed the rubber. You've deformed it, like it has expanded. You've deformed that rubber. Okay. So yeah.
Oh, just a quick question. So, what is that yield points?
Okay, the yield point is the part where it gets to the plastic. Then after the yield point, it will now get into the breaking point. So the it's like this. The graph for Hooke's law is like this. First of all, we have the elasticity, and then it moves, it keeps going, and it gets to our limit of proportionality, which is our K, our limit of proportionality, and then it keeps going, it keeps moving in, and then it gets to our Y, and from here it just moves into our breaking point and it scatters. It breaks or it cuts or it explodes or something. So the same thing with rubber, you keep on blowing the balloon or keep on blowing rubber to get to a point where it will reach the limit. From the limit, it gets to, it yields that, oh, I've given up on this part. I'm now plastic, please. Don't blow me further. And then just a little, you don't even need too much pressure. It will just break on its own. It will explode and break on its own. So it's the same part. Um, Yeah. It's the same thing with this limit of proportionality. So Hooke's law, talking about stress and strain, is strictly valid like when when we get um when we get to that limit of proportionality. So like a stress and strain graph, when it gets to the limit of proportionality, it means that at this point though, I'm no longer doing anything. At this point, I've been deformed. This is my end point. So there is no going further. So now, if you now check question 14 here, if you check question 14 now goes on to say, if you check it, okay, I'm not sharing that part, right?
That is so.
Okay, it says permanent deformation of a spring occurs when the applied load exceeds. So now you're going to be seeing something like, you'll be seeing something like limit of proportion. Don't let them confuse you. For limit of proportionality, it deals with where we're having the calculations and internal calculations within the rubber. Now, if the load should exceed if the load should exceed that elastic limit, the material enters the plastic region and it will no longer return to its original shape once the load is removed. So now the limit of proportionality is used in our calculations, which is our K, E, which is K, but the elastic limit is the permanent. That's why I was telling you that this limit of proportionality can also be like the elastic limit and all that. So when it gets to the elastic limit is deformed, that's where deformation occurs. That's where it turns out to be a plastic, or that's where it turns out to be deformed. I think we've all used rubber. It gets to the point where you just see that, oh, this thing has changed shape. It's at this shape now. It's no longer the original shape. So hooks is not really much stress like that. Would have gone deeper into hooks, but because of time, let's just let's move further. Let's move further. Okay. So just because of time, I would have loved to. One second. Mm, Okay. So let me just give a brief. So this is just what Robert Hooke is saying, that when we, yes, a question.
Oh, good afternoon, Gideon. I don't have a question. I want to ask if I can get the recording today.
Yeah, you can.
Oh, thank you. You guys should take care. See you. Bye.
Yeah, you can, of course.
Thanks.
Mhm. So let me just say this. Let's say I have, so this is it. We have an applied force. We have constant of proportionality, which is our K, and then we have E. All right, which is the elastic. So this is our spring constant, and that is F, which is the restoring force, and then we have our extension, which is E. Okay. So sometimes they include the negative sign because it means that we're restoring the force, or the force is going to be restored. So yeah, that's one of the thing about the Hooke's law. Now, where it breaks, it is important to know that it is not a
Sorry,
universal law.
sorry. I I missed the parts. Where did the negative sign come from?
Oh, the negative sign in this part is telling us that it can be moved back to its original position. This is elastic. The extension force is directly proportional to um. So the restoring force, okay, is proportional to that extension. So the if we can leave the rubber band, it gets back to its original position. That's what the negative sign is saying. All right. So this is how rubber or how spring they behave when you stretch or you compress them. Right. So you stretch something, it is directly related to how far it stretches, that extension. So if you leave it back, negative sign is saying that it's returned back to its original shape or its original. That's what that is saying. Now, it's very clear that in A-level physics. Now, um, the law breaks point, okay, where we have what is the limit of proportionality, which is what I'll just explain briefly now. Now, up to a certain point, this relationship is so sweet and it works well. But at one point here, our graph is going to start curving. Okay. At this point, the force now is no longer directly proportional to the extension. So it's not proportional to this extension. All right. Now the spring might still be able to snap back to its original shape. This is when limit of proportionality is this is limit of proportionality. So this is when limit of proportionality is exceeded. So at that point of limit of proportionality, it will reach a part where force is no longer directly proportional to the extension. Like, I mean, force might start getting more than the extension of that rubber band. But at this point here, it can break. Hello, Daniel. I will send it to you. I'll send it to you. And please stop. I'm in class. Text me instead. Okay. So, and this point here is the limit of proportionality when it is exceeded. So now at this limit of proportionality, we can still snap back and it will come back to its original position or its original shape. Okay. Then we have what we call the elastic limit. Now, at the elastic limit, if you keep pulling and pulling and pulling and pulling, you will reach what we call the elastic limit. And beyond this point, the material when it gets to the elastic limit is completely or permanently deformed. It undergoes what we call it the plastic deformation. So it means when you release it, Baba is not returning back to its original length. When it gets to elastic limit, it's gone. At this point here, that rubber band is already gone. So it's not returning back to its original length. So if you pull it far enough beyond this point, all right, if you pull it far enough beyond this point, you're now moving into what we call, it will yield at this side. You're now moving what we call the breaking point, where it explodes. So moving to what we call the breaking point, where it actually explodes. So where do we stop? Question. So this is what we're talking about. Say permanent deformation of a spring occurs when the applied load exceeds bam the elastic limit. Boom, it's already permanently deformed. It is permanently deformed. All right. Okay. So now let's check another one. That's question 15. Question 15 now says that, okay, what is the dynamic? You see, all the questions he said were actually kind of relatable. He said, what's the method of determining spring constant? What's the dynamic method of determining spring constant relies on what? That's what question 15 is saying. So I think this one is something we've done already. A spring constant. You know, whenever we talk about a spring constant, it means like it's just like you having a pendulum, all right? And then you are oscillating the bulb, or you are moving the bulb from one place to another on a spring. So now when you're moving a bulb on a spring, what happens is this. Let's say this is the spring, and you attach the bulb here, and you extend this bulb down. What happens? It keeps going up and down, completing its revolution. So it will bounce one, to and fro, one, two, like that, three. So this is also part of simple harmonic motion. Oh, don't forget, because it is completing oscillations and all that. So it relies on one of those principles. since we have period and we're going to be having frequency and all that. So it's not a circular motion. It's going to be, okay, I already said the answer. Okay. Okay, I already said the answer. Okay, so you guys should do this one. This one says the time period of a mass or spring system is given by what? I think you should know this one. Remember our simple harmonic motion, but this time around is for a spring. So it's something relatable. I know they just changed the whole some of the digits, but just know that in the spring, there is going to be a mass attached to the spring. Okay, so
I think it is B.
yes, it is B, where we have the 2 pi equals the root m over k. M is actually the mass of the, just as if we're relating it to L at this point here. Where is that our formula again? Yeah, just as if we're relating it to here. While K is actually our spring constant. Here now is no longer gravity. We're dealing with spring now. So K is our spring constant. Where is the, this where's my this is what I was talking about. So yeah, it is B. Our period for this spring is, the period is 2 pi root m over k. 2 pi root m over k. While for the one for simple pendulum is 2 pi root L over G. So,
The presentation screen.
oh, sorry. So the one for spring is 2 pi root m over k. So I've been here on the other screen since and I've been talking. And the other one is 2 pi root L over G for pendulum, while this one is 2 pi root m over G for spring. Okay. All right, so let's go to question 17. Let's see what question 17 is saying here. And okay. All right, so question 17 says here.
That's the question, please. Can you change the screen?
Okay, it says a non-zero intercept in a t square versus m graph or a spring experiment. Okay, you know when it was the one that has to do with the length of pendulum, it is t square versus L. Now it comes to spring, it is t square versus m. All right, so what does this tell us? The non-zero intercept. So what is the non-zero intercept in the t square? When we say non-zero intercept, it means that what we're plotting it against has to be the main thing. So yeah, what is the non-zero intercept?
A.
Effective mass of the spring. Yes, if it was t squared versus L, the non-zero intercept there is going to be the length of the pendulum, but this one is the effective mass of the spring. So let's get to question 18 here. It says the most critical precaution in Hooke's law experiment is to ensure that what? Or the most critical experiment in Hooke's law? We have to remember in Hooke's, we have to ensure that the loads are not so much. So we are, in order for us to take the readings of the elasticity of the material, we have to be, those loads, we have to be taking precautions of it. So what do you think is gonna be the answer? Yeah, C. Loads are added gradually. Correct. Yes. That's the most critical period. Loads are added gradually. And then for question 19, that's okay. See, we're almost done. I told you. So 1 o'clock. We try now. Sorry, my class sometimes used to take more than that. It says random errors in pendulum experiments are minimized by.
Taking repeated measurements.
Yes, you have to take repeated measurements so that you can minimize random errors. Maybe they bring questions like this for us, I beg. Sweet, sweet ones like this. I think the second semester, end of semester wasn't so difficult. All right. Then the ballistic pendulum method becomes unreliable for very small bullet masses because of what? We've talked about this like many times. Something becomes, we've said it multiple times. Yes, the angular deflection becomes too small. We've talked about the deflection getting too small, sine theta approximately equal to theta, meaning that the angular displacement becomes too small. It means that the degree will become too small. We've been having that too small. We said like 4 times, too small, too small. So those kind of questions should not even shake us at all. And yeah, so at this point here, I'm going to say thank you. I'll be releasing the maths videos after I've gotten permission from my people. So I'll be saying thank you so much for joining the class. And yeah, I'll be sending the recordings on the group so everybody will see it. All right.
Thank you very much.
Thank
You
you. We appreciate it.
you're welcome.
Thank you. Thank you.
So are
Right.
you in 300 level?
No, I'm not in 300 level, but I have 9 years experience of teaching, and so I'm in your level.
Okay, 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 okay. I understand now.
Yeah, yeah. All right. So good luck, guys. And yeah, I'll soon let me see what they will say about the maths, and we'll know if we're releasing it. Right. So go and have fun. Sorry, I took your time. Go and beat. Go and eat. Go and arrange yourself and all that. So see you next time. Bye.
When would the next time be?
I'll be in the group now. My name is Gideon Wakama, so aka Educational Access. You just know me. I'll be in the group, so you can reach out to me most times if you have
Okay.
questions and all. Mhm. All right.
All right,
See you
all right.
guys.
Thanks. Thank you very much.
Yeah. Bye. More Scrabble games. It seems like you've met me before. Okay.